Whoa, more than 100 people are watching us right now. Welcome all. Welcome to the DSC Medipol's biggest organization, Medipol Global Summit, which we are going to cover many fields within 3 days with many expert speakers. In addition to our technical speakers, we will have 2 keynote speakers in this Medipol Global Summit. Again, thank you very much. Thank you, guys. Welcome, guys. How are you?
Great. How are you guys doing?
Actually, today, as I mentioned, we had 2 keynote speakers, but Merve İşler had an internet problem in Los Angeles. So Merve has recorded a video for you, and we are going to display her video on the screen after a while. And after that, we will invite Professor Dr. Hasan Fehmi Ateş from Istanbul Medipol University. And then we will pass to do our sessions, technical sessions. Firstly, we are going to start with Luca Anisin. And I want to mention about the details of Medipol Global Summit, what Medipol Global Summit is, and what kind of opportunities do we have today and the upcoming days. Again, welcome, guys. I want you to introduce yourself, and after that, firstly, İlknur, I want you to introduce yourself, and after that, please mention about today's schedule, what kind of sessions and speakers do we have today?
Hi everyone, I'm İlknur Akçay from Medipol University, Department of Computer Engineering and Biomedical Engineering. Today's schedule is as follows. Firstly, Professor Hasan Fehmi Ateş and Merve İşler will make a keynote presentation. After that, Luca Anisin will be with us 13 with the Introduction to Machine Learning section. Guan Wang will continue with Neural Network presentation at 14. And finally, Brett Conans will share his presentation of Artificial Intelligence with us at 16.
Thank you very much, İlknur. What about second day? What kind of sessions do we have for on Saturday, Zishan? Could you please mention about it?
I'm glad you asked. Firstly, I'm Seniha Zishan Zülfikar. I'm studying computer engineering at Medipol University. Moving on to the second day schedule, at 13 we have Malik Malkavi. He's going to be talking about cybersecurity power between past and future. Then at 14, Abdullah Ismailov will speak about what a cybersecurity expert does. Then at 15, Amin Altahir will introduce us to blockchain technology. And at 16, it will talk about the future of blockchain technology.
Thank you very much.
Lastly,
sorry. Yes, Tofi.
At 17, we have Topik Sahir. He will talk about software development lifecycle and hackathons.
Yes, thank you very much. Again, personally, I'm really interested in blockchain technology. I'm waiting tomorrow's sessions. And actually, I was dealing with the cybersecurity before, I guess, 7 or 8 years ago when I was a kid. And Tofi has a really, really important session, who is the CEO of Arkis Academy, which is our platinum sponsor of this Medipol Global Summit. And please don't miss these all important sessions tomorrow. And as I mentioned, Tofi will mention about the endurance, which is gonna be done at the end of the May as a hackathon. So thank you, Zishan. Again, Emre, please, could you explain the last day of Medipol Global Summit?
Hello, everyone. My name is Emre Kan Satış from DSC Medipol University. In the last day of the Medipol Global Summit, we will have 4 speakers. Juan Herrera will be with us at 13 o'clock with his roadmap of a front-end developer in 2021 presentation. Then at 14 o'clock, Maxim Salnikov will talk about progressive web applications. After Maxim's presentation, Muhammed Salih Güler will share his knowledge about Flutter at 15 o'clock. And in the last section in the summit, Nelson Glauber will say goodbye to you with the Jetpack Compose for Android.
Thank you very much, Emre. And everyone was asking about the certificates on the live chat. I want to mention about the certificates because there are 5 different certificates, and right now Gusal will mention about it.
Exactly. Thanks for actually asking, Berkay. I've also seen in the chat we have a lot of questions regarding the certificates. So, guys, certificates, you are not actually limited. Just start mentioning that you are not supposed to attend all 3 days in order to get the attendance certificate, but it's going to be at the end of each section. So all you have to do is today attend all the 3 sections, and at the end of them, you're going to be given 15 minutes to submit the form, where we are asked gently to get your first name, last name, and final the email where you would actually like to get the final certificate mailed to. So please attend all the 3 submission, all the forms. Else, unfortunately, if you're going to miss any of them, unfortunately, we're not going to be sending you the final certificates. So that's how it's going to be working for the first day. And I would like to also continue with the second and third day at the end of today's sessions.
Thank you very much, Vusal. As Vusal mentioned, guys, please don't forget to fill out the form at the end of each session. And what about the giveaways? We have shared many giveaways through our Instagram page. Yusuf, could you please introduce yourself and after that mention about the giveaways?
Thanks for asking, Berkay. First of all, hello everyone. Welcome to Medipol Global Summit. I don't want to waste your time because there is a really exciting summit awaiting you, but let me introduce myself briefly. My name is Yusuf Benli. I am a second-year computer engineering student at Istanbul Medipol University, and I am a core member at Medipol Developer Student Club. I want to inform you about our giveaways. As you have seen in the intro and description, we have a lot of giveaways from different companies, which are Euroshare, Hamstaff Sale, Kahve Gibi Kahve, JetBrains, and us. The conditions are written under the post, and I recommend you to check our DSG Medipol Instagram account. But if you missed or didn't understand something, you can ask your questions from the chat area during the summit. And I wish you all a good and quality time. And that's all, Berkay. Thank you.
Thank you very much. So as you can see, there are lots of opportunities under the Medipol Global Summit, and don't miss any of these opportunities, please. But I want to mention about another opportunity of this summit, which is the surprise links. We are going to send a surprise links through between the sessions. Actually, we don't have a certain time, but please don't forget to fill the surprise links that we will send you through WhatsApp groups and on the live chat, of course. And please join our WhatsApp groups. You can reach our important links, such as WhatsApp groups, through our link tree, and moderators are going to share our link tree through chat after a while. And before inviting Professor Dr. Hasan Fehmi Ateş, I want to display Merve İşler's recording. Merve İşler has a message for you, but it was recorded in Turkish. So after 1 minute, we will invite Hasan Fehmi Ateş.
Evet, herkese merhaba. Güzel bir cumartesi günü diliyorum hepinize. Ben Merve İşler, Google'da geliştirici ilişkileri koordinatörü olarak çalışıyorum. Ve DSE Medipol Üniversitesi'nde öncelikle böyle güzel bir etkinliği organize ettikleri için çok teşekkür ediyorum. Başta liderine, Berkay'a ve daha sonrasında da bütün core ekibe emekleri için ve çok güzel bir ajanda hazırladıkları için, bu hafta sonunu dolu dolu geçireceğimiz için çok teşekkürler. Normalde bu yayına canlı olarak katılmayı çok istemiştim. Ancak şu anda bulunduğum hem saat diliminden dolayı hem de teknik bazı sıkıntılardan dolayı canlı yayında problem yaşayabiliriz diye video göndermek istedim. Ama tabii ki herhangi bir sorunuz olursa veya Google toplulukları hakkında daha fazla bilgi almak isterseniz bana ulaşabilirsiniz. Bununla beraber de şu anda zaten bu etkinlik Global Summit, DSE Medipol Global Summit aslında Developer Student Club'ların, yani üniversite bazlı öğrenci topluluklarının hazırladığı bir etkinlik ve bununla beraber de eğer siz de bir öğrenci topluluğunun parçası olmak veya lideri olmak istiyorsanız aslında şu anda başvurularımız devam ediyor. Ve liderlik için 1 Haziran'a kadar başvurabilirsiniz. Bununla alakalı da developers.google.com üzerinde communities kısmına girerseniz, belki birazdan size zaten bununla alakalı link gösterir Berkay. Oradan başvurabilirsiniz. Bununla beraber de diğer Google toplulukları vesaire bunlarla alakalı da bilgi almak için benim profilimi ziyaret edebilirsiniz. Bu konuda birçok şey paylaşıyorum. Çok teşekkür ederim. Harika bir gün olsun hepiniz için. Kendinize çok iyi bakın. Hoşça kalın.
Merve, thank you very much. As Merve mentioned, I am sending the dsccommunity.dev link right now through live chat, and you can reach there and find your DSC at your campus, and maybe you can be a part of the Google communities for next year or upcoming years, and you can be a leader of your university. So I want to invite other keynote speaker, Hasan Fehmi Ateş, Professor Dr. Hasan Fehmi Ateş, now. Hello, Professor. How are you? Thanks for accepting our invitation firstly.
Sure. Thank you. Thank you for inviting me. And I hope you have a very good summit. I'm happy to be part of this activity. And I'm a professor at the Department of Computer Engineering at Medipol University. And I'm also an advisor to the Computer Engineering Student Club. I'm very happy to see that Medipol Computer Engineering Student Club is organizing such a useful summit. And the content, I'm looking at the content, it's, I think, very useful and very up-to-date. Very important topics today in machine learning, neural networks, artificial intelligence, and the other days, cybersecurity, blockchain. In Medipol, especially, we focus on and we put a special emphasis on artificial intelligence, machine learning, deep learning, and the applications in different fields such as computer vision, image processing, natural language processing. And I'm happy to see that as a student club in this global summit, you have placed a special emphasis on these topics. And I wish you all a very successful summit. And thank you again for this opportunity.
Thank you, Professor. All of us know that you are giving some lectures about deep learning, machine learning, and as you see, we are going to cover artificial intelligence in machine learning and neural networks today. Do you have any advice to audience who are waiting today's session?
Advice? I couldn't hear exactly.
Yeah. Do you have any advice for who want to enter to machine learning world? Artificial intelligence world, who are waiting us from audience right now?
Yeah, so the machine learning and deep learning in particular is like an ocean right now, and we have many open source, open resources available at the tip of our fingers. So it's very too easy to access these resources and learn a lot. But my advice would be to be also to practice what you learned. So it's not just enough to learn these issues and topics, but to actually start up with some projects and implement solutions and really experience, because this field is based more on experience than theory, maybe. So my advice would be also to maybe have workshops in the future for different machine learning applications. That could be a good idea.
Thank you very much, Professor. We are very glad to start such a big organization of DSC Medipol in its first year as a community. And again, thank you very much to be part of this Medipol Global Summit.
All right, have a good summit.
Thank you very much. And after 2 minutes intro, you can reach our links and you can join the giveaways through our LinkedIn page. And after 2 minutes intro, we are going to invite Luca Anisin for the first session. Thank you very much again.
Welcome, Luca.
Hello, Luca. Welcome. How are you?
Thank you very much. I'm doing pretty well. How about you?
We are good. Thanks for accepting our invitation. Firstly, thank you very much for joining us today.
Yeah, thank you for your invite, and I'm really glad to be with you guys and with everybody in the chat. I don't know how many people we have now in the chat.
More than 150 people are watching us.
Welcome, everyone.
Yeah, Luca, please, could you explain your content, what you are going to cover today?
Yeah, so in about an hour and a half, I'll try to keep the content a bit shorter, so we have more time for questions and answers, and I think that provides more value from my side. We are going to talk about machine learning, what it is, what it isn't. I'm going to answer your questions on maybe how to enter this area, because I know that some of you are students, maybe you're from other areas as well, and that is really common to see people from economy, from marketing and sales nowadays going to machine learning and data science. So this will be like a light introduction to machine learning. We are going to speak about its applications. I'm going to use one tool, maybe you heard of it, Quick Draw, and to use that as an example to how to use data and how to train some machine learning algorithm and what machine learning algorithm really is. So that's the topic. Yeah.
Thank you very much, Luca. You can, if you are ready, you can share your screen. But when you share your screen, and we are gonna show on the screen your screen, can you please check your sound if there is any sound problem? Usal, what do you think? Is there any sound problem from Luca?
I think I'm actually using headphones. That's why it's fine for me, but I don't know about the people are using without the headphones.
So I can change to other microphone if you prefer that.
If you can, it would be great, and we can maybe show the intro one more time.
Let's do that. Let me give you a second. Okay, so.
So guys, after 30 seconds, we are gonna start.
How about now? Can you hear me better?
Yes, very nice, very nice.
Amazing.
Very nice.
By the way, Luca, actually, feel free to introduce yourself, your background, where do you work right now, and so on right now also.
Yeah, cool. So should I do the introduction of the topic again, or should I introduce myself before?
And just introduce yourself. That's going to be enough.
Okay, cool. So as you already know, my name is Luca, and I'm coming from Serbia. I've been in the industry about 4 to 5 years, so I'm close to senior, let's say something like that. I've been working on many different projects, from optimizing electricity grid to computer vision applications such as OCR in the real world, cars, chassis recognition. Then I done optimization for some websites with machine learning, energy optimization and prediction, and so a lot of applications. Currently, in the last year, I've been working on my startup called Scooby AI, which I think you can see on the website of this conference as well. So the idea of that website the startup is to connect you job seekers with data science opportunities around the world, and then help you in the process of finding the job.
Luca, by the way, how many students do you have on Udemy?
About 230,000 right now. Yeah.
It was an amazing. When we research you on the internet, and when we see the number of students that we were shocked.
We were shocked, actually. Yeah.
Yeah. So, it happened. And I don't know if it's naturally, but so I had a lot of help with Adlan and Kirill. Probably you heard of them. They had a very big courses such as Machine Learning A to Z and other courses as well. Yeah.
So, okay, if you are ready, you can lead the stage and by sharing your screen.
Cool. So, okay.
And maybe, by the way, at that time, maybe we can share the Luca's course, the Udemy course, on the live chat, right?
Can you see my screen?
Yes.
Okay, cool. So I shared my browser. I'll be opening some applications along the way. So by the way, the content will be broken down to some sections. So after one section is passed, you can ask the questions, and I'll try to answer before we jump to the next one. At the end, there will be some time for questions as well. So yeah.
All right, great. The stage is completely yours, Luca. Good luck.
Cool. Thank you very much.
Bye bye.
So, as we already spoken about this, we are talking about machine learning. And do you guys know what machine learning is? Have you had experience with machine learning before? Can you please write in the chat? I think there is some delay between YouTube and my platform, but yeah. Okay, so yeah, probably there is some delay. We can discuss that in a bit. Here is the YouTube video. I'm not sure if the sound from this video will be heard with the stream. Let's check. Okay. Can you hear it?
No, we can.
Yeah, you cannot. So yeah, I'll recommend, if you want, to go to this Oxford Sparks what is machine learning after this section and look for this presentation. It's amazing. Like in 2 minutes they describe the whole content and what machine learning is. But because you can't hear it now, I'll just explain. So in the general sense, when we are children, and this is a child that you can see here, we are learning by recognizing patterns and by repeating some actions many times. And in other sense, we don't know what we are doing in the very beginning. So when we are born, we only see basically what is given to us by our parents, by our friends later on. And yeah, so basically that's something that we wanted to translate to a computer as well. So machine learning comes into that sense. We are providing a lot of samples, and we are going to discuss what those samples are and how to provide those to the machine in a bit. But basically, by seeing a lot of samples and repeating an action, and we are correcting that. So you know that when you were a child, your parents constantly tell you, don't do that or do that. And that's basically what we are telling to an algorithm or a computer to repeat. And by repeating an action that we really wanted them to, we get something that can be used by other users, and our computer learned. So it's kind of a magic right now, and I know that for somebody that didn't have a chance to work with machine learning, it sounds amazing. And trust me, I've been working with machine learning for a long time now, and sometimes it's really amazing what it can do. So yeah, the whole video explains that analogy. But before I jump to the explaining how actually machine learning works, I would like to ask you to go to this link. I'll do it right now by myself, but if you want to test it yourself, that's fine as well. So I'll take a few minutes to experiment with this platform. This platform is called QuickDraw. So the link for this is g.co/QuickDraw. If you can copy this link to the chat, it would be amazing. And basically, it is application created by Google AI, which tries to explain how neural networks are working by, in a real time, predicting what you are drawing. So let's try it. So when you click Let Draw, I get an object that I need to draw in under 20 seconds. So let's try it. By drawing, my computer will tell, okay, I see a line, so that's fine. And then if I add something like this is a skyscraper. Then if I add a flame, it recognizes it's a flame. And you can go in many different ways. Let's try another one, and let's try to draw something like this. And yeah, so by recognizing that, you already saw that when I draw one part of it, it will say, oh yeah, it's something that I resemble to be a line. If I add more details to it, it will tell me, oh yeah, I I see that it might look as a skyscraper. If I add more details, such as flame at the top, it will recognize something more. And that will happen until it reaches to the object that I was about to draw. In my case, it's a candle, or in any of yours cases. But how it's done? Yeah, it's amazing. So yeah, thank you for the comment. But yeah, I'm pretty surprised it's working that fast. So there are a couple of questions to answer right now about this game. So how does it work? How it works? How is it recognizing your drawings? Like, okay, you already saw that it's recognizing step by step, but is it really like pattern matching or something like that? Or how could we program this? And there are many ways to program this, and we'll discuss a couple of ways, the old one and the new one with machine learning. So let's answer the first question. How do we do this? How does the ML behind this application works? So if you go to this link, or if you are already on the site, you will have this world's largest doodling data set. So you can click on it, and it will take you to the link to see all the data they have and use to train this machine learning algorithm. There are so many objects, as you can see. Like this is zebra, zigzag, then yeah, parrot, necklace, like so many of them. If we enter, let's say it is a bar. Okay, cool. Let's go to the bar. You can see that all example of barns drawn by other people in the world. And yeah, all of these are connected with a barn. So you can already see that if you want to train a machine learning algorithm, we need a lot of examples of a one object. So in this case, it's a barn. But that's basically okay. Let me try to. Oh, okay, cool. So we have a lot of examples, and in this image of here, you can see a lot of examples of a carrot. I assume it's a carrot, and I think we as humans can do this pattern matching really well and really fast. But how do we program this, or how do we make it? How do we make this? The one idea that I can see here, and one problem that we are going to discuss in a bit, is we need to have some things that repeat one after the other. So as you can see here, on each carrot, we have a triangular shape. Sometimes it looks like a pizza slice, like this one, but yeah, it's not. It's a carrot. And then on top of it, you have some lines that comes together, and they should represent a grass or a leaves of a carrot. So all this is basically what we as a children are doing. Like, we are seeing a lot of things basically multiple times, and until we reach the point and then our parents say, oh yeah, that's right, this is a color blue, this is a color orange. And in this case, we use those features from carrots, for example, to say, okay, so if you see these features in an image, let's say it's a carrot. Okay, so how do we actually recognize these features, and how do we program this? So whenever you try to create an application, there are some goal. In this case, we have a goal to recognize a object that's been drawn in front of us. And that's fine. We know this part. But how actually to engineer this? The old way, the programming way, is basically to create a function or create a piece of code that will be dedicated to each feature in our object. And let me give you a perspective this. If you programmed before, you know that if you wanted to check a password, you wanted to check whether or not the password has a capital letter, a small letter, exact number of letters. And for each of those checks, you would create something like this. If your password has length of 10 plus characters, then we say, oh yeah, it's a strong password. If it is less than that, please add a few more characters, and so on. But what happens when we work with images? It's coming so harder. It becomes really hard. And in that case, how do we actually create these parts of the code, pieces of a code that will be dedicated for a caret, that will be dedicated for this part of a caret right here, or to recognize this triangular shape? Or what happens if we add something like this? It's not triangular anymore. So when you have an image and you want to work with it, you need to create a code that will be dedicated for each part of the image separately. And what I mean by that, you would need to create a part of a code that recognize that top part of the caret or color of a caret if we worked with colors. Let's give you another example with the cats. So if you wanted to recognize a cat, you wanted to create a function, let's say, to recognize two triangular shapes that are pointing upwards, and that will be ears of a cat. Then below that, you wanted to have two circles or ellipses, that would be their eyes. Then below that, you would have some other triangular shape, which would be a nose of a cat, and so on. So for each part of a cat, you would create a function, and basically, if you say, okay, this is the present in the image, that's amazing, it's a cat. And that will work perfectly for that image. But what if we add another image? That cat is not standing like this, but a bit shifted, or few pixels in the size. When you're working with images, it's becoming really hard, really difficult to make those patterns or cases for all things that can happen in an image. Like especially with cats, if you worked or looked for some cat videos online, you will see a lot of crazy positions that you can find your cat sitting or laying down or something like that, which is really difficult to program everything in the code. And that's where machine learning kicks in. In machine learning sense, you write one algorithm that has some parameters inside of it. Let's not go to that much details right now. And by giving a lot of examples, same as our child in the previous video, you get an object recognized every single time or most of the times as a caret. What if you need another object? So yeah, let's give the same amount or similar amount of images for, let's say, potato right now. And then your machine learning algorithm will recognize between caret and potato because you gave two different objects that recognize two different parts, two different things. One case is a caret, the other case is a potato. And you can do as many objects as you want, as soon as far as you have enough images for each or examples. So that's where machine learning comes. In a quick draw example, as you saw in the data part of it, you have a lot of thousands or even hundreds of thousands of images. To be precise, for all objects together, you have, I think, 50 million images of doodles drawn by people that they use to train a machine learning algorithm to recognize your drawing in real time. And that's how their machine learning algorithm works. The type of algorithm is called neural network, and we are going to touch upon it a bit later. And in the next section, you have that. So now we have a decision to make. Do we actually go in a sense of everything that is possible, everything is hard, go with machine learning? Or there are some other approaches that still work really well, and that is a rule-based system or old-way programming system. So, yeah, exactly. No, we are not going with machine learning every time because some parts, some tasks are really much suited for classical way. And let's do this question together. How would you solve this sorting of song title? Would you use a rule-based system or machine learning? Can I open YouTube stream? Maybe it's faster for me to to see your answers. I never worked with a live stream on YouTube, so it's a bit like messy here. Okay, cool. So what about hybrid way? Exactly, that's an amazing question, and we'll have one example in a bit, in a couple of seconds, I think. So this one is a rules-based, and let me tell you why. In machine learning, you have, yeah, exactly. A rule-based system is much faster here because you have set of rules and set of alphabetically sorted songs. So you have already predefined algorithms to sort these songs. Don't be sad, Yunus. Sorry, I don't know if I pronounced your name correctly, but yeah, it's fine. We are learning together right now, so no worries. Machine learning is overkill here, and it won't provide much value. But the rule-based system, there are so like many things that you can say, okay, let's look for a first character in a song title and then sort it by it. But then you can, yeah, thank you. I tried. So yeah, you have like predefined algorithms for sorting the songs. Then you use them and sort them. So machine learning is not needed here. What about ranking web search results for Google, for example? This example is a bit harder. Yeah, exactly. That is the right. So ML is amazing for recommendation, and they are so good in like in Spotify and Deezer, for example. Yeah, ML is used here. Okay, let me hear more. Okay, machine learning, cool. Yeah, you're all correct. And rule-based as well. So somebody mentioned hybrid, and machine learning is primarily used here. So everybody who said machine learning is correct. And rule-based is used as well. So let me tell you why. So first we use machine learning to find what is something that you really want, and that's coming to recommendation. And yeah, learning to rank is amazing, amazing paper about this. So basically, you go and do some content related stuff like recognizing what you watched previously, what clicks you had on Google, and then recommending what is similar to that. And for example, if I wanted to recommend news to you, I would go and do that first. But after that, I would like to recommend and sort those by dates. So I would prefer to give you the most relevant news that are newest news. So those newest news will come from the rules-based system that are previously selected by machine learning. So in this case, it's a mix, but primarily used by machine learning. What about predicting house prices? And if you worked on machine learning before, okay, so I already gave you this answer. Yeah, it's machine learning, but yeah, this is really famous data set. So most of you probably worked about this. But yes, machine learning is used here. There can be rules-based systems in like insurance companies. They're using some rule-based things. That is old way to doing this. There's so many moving parts. Yeah, regression. We are going to speak about types of machine learning in a bit, but regression would be the solution here. Amazing. And processing online payments. How about this? Okay, so yeah, everybody who yeah, exactly. So it's predefined. It is really easy to solve. Somebody said both. Yeah, it is. It can be both. There are some like parts, and you're right as well. as well. Sorry. So rule-based system, everybody who said that is correct, because like the processing of online payment is rule-based system. There are predefined algorithms to handle this. Like big systems such as Magento is using this, and you don't really have to care about this. But there is one part, small part, and very important part used by machine learning here, and that is fraud detection. So if you want to do some your projects on the side that you want to practice working with data, that would be fraud detection. That's my recommendation, and you can learn a lot. It's intermediate project. Don't start with it. But yeah, that would be a machine learning part with this. I'll just skip this part, but basically you probably all know that classifying an object in a photo, we already spoken about this, and that's quick draw, and that is machine learning. So yeah, there are many different like examples for rule-based system, machine learning, and each of them has its benefits. I wouldn't go for machine learning every single time because it introduces a lot of unknowns. So for business especially, like it's really difficult to sometimes switch to machine learning from rules-based system, especially for something as a bank. But yeah, so each of these approaches don't discourage one of the others. So if you're doing a rule-based system in your company, it can be really well as well. So you don't have to switch to machine learning like just for the sake of switching. But using machine learning has its advantages, yes. So yeah, before we jump to the implementation side and speaking to about the next section, do we have some questions or so far? Okay, not for now. There are two videos here, and yeah, okay. There are two videos that I'll send afterwards to organizers, so you can have that. But yeah, basically, let's not watch them because of the sound. So we give you info. Are you okay? So yes, Ari Robot checks right. They're using you or everybody from like myself, everybody to mark their data set. So, and that is amazing point right now, because we are going to speak about collecting data in a second. So yes, if you had the chance to check like multiple images before joining some site, they are using us to collect data for Google, for other companies as well. So yeah, but hey, it's protecting something. I don't know what, but yeah, it is. So let's speak about machine learning process. I love machine learning. So when I started working in IT, I always was focused on user first. So I love to deliver value. I love to speak about value and always have a consumer in mind. And this is something that you should have, and I don't want to say must have. It's not a must, but it will provide you an easier path to success if you have a consumer in mind. What I mean by that is this. When you're creating a machine learning system, you are giving that to somebody. So it can be internal system in a company. It can be still somebody from that company will be influenced by the system. You can have like a recommendation system for Google ranking. Everybody of us here in the chat was influenced later or before by that system. Then Google Translate, everybody's using that. So you have some other user that's going to use your predictions or your machine learning algorithm trained on your data for some use that you intended to use. So you always start with a user. Then you start with their pain points, recognize their pain points and say, okay, so let's use an example of translating data. So you have us here. I don't know Turkish, sorry for that. So I wanted to communicate with you. And somebody from you don't know English that well, so I wanted to speak directly in Turkish. So I went to Google and searched for translate. Then they recognized that I searched for that, and oh yeah, there is some user wanted to translate from Serbian to Turkish or English to Turkish, and there is no such a service. So yeah, I have a pain point, let's solve it. Then they use that pain point to define an objective. Defining an objective can be delivered directly from a user side. It can be internal, but you need some goal to solve. In this case, you have a goal to translate one language to the other, or many languages from one to the other. Then when you define that objective clearly, defining the objective, it will help you a lot in the implementation side. You go and collect data. So collecting data is boring process. Trust me, I sometimes I hate it, but that is something that will take you 80% of the time. Like it is the biggest part of your project. And trust me when I tell you it is the most important part. So collecting data is, I would argue, it's more important than prediction, and not prediction, but training a model itself. Training a model will come after that, but collecting data and having a good data set is a crucial step. So what I mean by that is, if you have wrong data, if you have a garbage data, you know that saying, you probably read it on many blog posts right now about machine learning: garbage in, garbage out. So what I mean by that is, if you have garbage data, which is wrongly collected, didn't labeled, so not for that task, there are many different scenarios that you can have wrong data, then your model will be the same, not good enough. So you start by collecting data, you dedicate a lot of time to curate your data set to be perfect or close to perfect, and then you use that to train your model. Train model comes really easily after that, and I would say naturally. So you have a data set, you have a goal, you have your targets that can be, for example, in our case of quick draw, if you draw a carrot, let me recognize a carrot, and that's simple. So you have a training part, and yeah, you train the model, test it, and do some predictions. Now, I really skipped over this testing the model. So if you never worked with machine learning, you have to test your model. And let me walk you through one example. So if we had a data set of 50 million quick draw or doodles to train your model on, it would be amazing if we can dedicate and say, okay, let's use all 50 million to train our model, but that would be wrong. And why is that? Well, let's dial back a few minutes. We talked about user, and the goal of the whole process that we are talking about right now is to help some users solve their problem. In this case of quick draw, we want to help user have fun, to learn about machine learning by using a quick draw application. So, but they really want to use that without us, that we created a system monitoring them while drawing. You know, it would be pretty weird if you're sitting above their heads and checking, okay, don't draw a carrot like that, it won't recognize a carrot. That would be pretty limiting. So instead, you want to test your model in-house before giving that to a user and to test it finally. So you want your model to be generalized. What I mean by that is, when you train your model, you want to work on some data that it's never seen before. Like you train a model on 40 million examples, and you want to that model to be exactly good as on the training part as on those 10 million examples that you never given to the model. And that is called testing the model. So whenever you try to teach a machine learning model to do something, whatever is the task, you want to keep one data locked in a safe, if possibly. That is called testing part. Somewhere you will hold out set, and that is interchangeably used. And you want to train on the training part. Pretty simple. So you train it, you get some results on it, and then you put your testing data into that model and get some results. And you say, oh, it's pretty scalable. It's working pretty well. So in that case, you want that model to work. And if you have your model working on the training testing part, you can arguably say that it's good enough for our users and then put it in the production after that. And that's where your predict and evaluate comes. So if your predict and evaluate, you can see this arrow below, have bad results. You go back in the collecting stage and either get more data, label it better, or you can say, oh, it's working well. Let's go back to our user and put it in a great use. So this is how your every single machine learning process works. And this represents here an iterative process. So you don't know at first whether or not your machine learning will be good, whether or not you will have some good results or not. So sometimes you will get really bad results, and then you need to work a lot on your data and then come back, maybe change your model, and then make some other predictions. So it is really a research-based way. So now we talked. This is amazing video about human bias, and somebody mentioned collecting data, and this video sums up that. We can't listen to it because it's a really talking video and not visual one. So if you have time after this, go check it out. But what it explains is when you collect data, we are humans, everybody in the chat. I hope so. Like we have something. Are we AI? Well, or are we robot? I don't know. I don't know. Maybe I am, but for now I am human, and we make mistakes. Everybody does. And when we collect data, we are not making intentional mistakes in a sense like making some label wrong or intentionally, but you have some background from your country, from your friends, from your family. I do. Everybody does. And when you label data, you will end up having some bias in your data set. So let me give you an example of bias. It can be, let's say, in Asia, most people will be Asian. So if you're creating a face recognition system, that face recognition system will be the worst one for us from Europe. And yeah, that's basically it. In America, they really need to care about like the diversification of races and other people and the genders and everybody, because everybody care about that, and for a good reason, because they are so very big bias inside very big data sets from big corporations. So we as humans make mistakes, and you can learn that from that iteration process, and it's really hard to distinguish those biases, but they exist. So be aware of that, and when collecting data, there should be a few people checking that data set, not only you, because of that reason only. Yeah. And the other video, because there are two videos that I skipped, is about the privacy of data. So right now, there's GDPR. You maybe heard of it. That is General Data Protection, GDPR. Okay, I don't know, regulations, I think. Yeah. So that's basically saying I consent to this. I consent to give you my soul when I register on Google, and yeah, all that fancy stuff that we done together. So basically, you want, when you're working with data, to work in an environment to secure the data and not provide like crucial information. If you're specifically working in the medical domain, you don't want to share the data for any reason to anybody outside of that project, because obviously so yeah, it's the most important part of the business, you know. So you're working with some company, that company can live or die because of the data, and also users are really influenced by leaking data. And you heard probably about a recent leakage of data from Facebook. So yeah, Facebook has done bad things about their data protection. So yes, now we are going to discuss what machine learning can do. Do you have any questions before? Okay, Yunus, can you please ask this question at the end? I'll need to think about the good answer to this question, and it can be a bit longer. The other question is, what is the difference between testing and validation? Amazing question. So if you worked before, you have like a terminology of validation set. So there are actually 3 parts, and I didn't mention that right now because I didn't want to go into that detail, but that's fine. So we have a training part and a testing part. First, let's talk about testing. Testing part is something that you lock in your safe and don't, for any reason, to try to put it in your model. So this is something that you want to keep until the end before you put your model in production. Okay. Now you have a training set that is unlocked and ready to be used by your model or models, depending on what you're creating. So that being said, that training part really wants to have most edge cases or diverse data that could be coming in production later on by users. So that's something that you want to recognize by testing. Now you have a training part. You take one part, small part of the training set, and you call it validation set. So you don't actually train it on that small part, but you can constantly check your model while training to see how it works on that validation set, which is not locked. It can leak some information into training set. So your model will provide decent metric results on that validation part, but you're not really caring that much of like how accurately you created the validation set. So when you're putting something in production, you always want to have that testing data set never seen before by your model, leave it at the end, and then you focus on training and validating your model while training process is done. So that's a difference. Sorry. So validation set is taken from training set. Okay, cool. So when you go online, you will see a lot of terminology from machine learning, a lot of buzzwords like, oh yeah, artificial intelligence is this, machine learning, deep learning, reinforcement learning. There's so many terminology. What actually it is. So AI is a big area of research of computer science, and it's really old. Like if you go into papers, you can find out some AI papers from 60s. And that really came together with like a lot of, even they worked with the text in 60s in IBM, creating their first chatbot or something like that. So yeah, it's pretty old. It's not new stories. But yeah, there's something called AI winter that happened in late 80s, early 90s. And yeah, everything is considered to be part of this AI AR sphere. So artificial intelligence is, as I said, a subset of computer science that has all systems, including machine learning that we already talked about. But AI has a bit more algorithms that can be rule-based. So we talked about rules-based systems. Some AI systems can be recognized. Some systems can be described as AI system, even though they are only rules-based systems. Like regex systems can be recognized as AI. Then they are planning, path finding, like for example, Google Maps. When you select the fastest route from point A to point B, you will find out that route, the optimal route, is not found by machine learning, but a graph search. So you have some structures called graphs, and we are not going to talk about them right now, but finding an optimal path from one part to the other in that graph is considered to be AI as well. So there are so many ways to describe what AI is, but something that we most commonly see right now is coming from machine learning, because machine learning is based on actually using data and optimizing that algorithm to learn over time and improve itself. So we saw one example about Quick Draw. There is Google Search. There is Google Translate. There is a Facebook whole news feed, and like spam detection in Gmail. So many different things. So every single part of that is considered to be a machine learning. And there is a deep learning that is coming to life most recently. I would say not longer than 10 years, but we have papers about neural networks much older than that. And that deep learning is the difference between machine learning and deep learning is only in the type of algorithm. So that's the main difference. We have one question. Okay. Okay, so yeah, that's a good question. So reinforcement learning is, I would say, a subset of things happening in artificial intelligence and using machine learning and deep learning algorithms. So it's kind of subset of all these areas together to solve problems that can be solved in the sense of just optimizing and saying, this is an image, this is a cat, and using the traditional way from machine learning and deep learning. But there is that really learning part in the process where you teach your algorithm in the same way that you would for a child. So you're giving an example and basically giving a cookie and saying, okay, yeah, this is a good behavior or this is a bad behavior. So that's how you teach algorithms in reinforcement learning. And because of underlying structures, you're considering them to be a part of machine learning or deep learning. What is the difference between data science and machine learning? Okay, great question. So data science is a much broader part, much broader of AI, machine learning, and deep learning. There are so many different areas, and the next part will explain that a bit. So big data is a subpart. I would myself classify it as a subpart of data science. So data science consists of a lot of techniques to work with data, data analytics, statistics, finding insights from data, business insights as well. Machine learning is a really niche thing about that. So when you have a data processed, analyzed, you want to use the data to make some predictions. So ML is trying to predict what is in the future, and data science is trying to find underlying structure of data and do some analysis. But generally, data science is really big and consists all of these things together. So yes, big data is also part, I would say, part of data science. Which programming language is more useful to us, and where should we start? So that's a big question. I will answer the second part, where should we start, at the end, but just for a programming language. So for machine learning, I would recommend Python. There are other languages as well. But Python is most friendly programming language to learn right now. There are some improvements in the area of C++ applications and all, but I would say that C++ is really hard to learn and master because there are so many moving parts that beginner or even intermediate should care about before even considering machine learning in that. But yes, I would do Python classify as a first, and for other areas, we can do other programming languages as well, and we can discuss that at the end. Cool. So at this slide, we have like ML as the center of algorithms, technology, and big data. So when we say algorithms, it's really logical. There are so many. That is driving force of machine learning, actually. So, well, big data and algorithms. Algorithms will provide insights such as like what type of data you have, which algorithm to apply, and there are so many mathematical models that we can use that are now considered to be as a part of machine learning to train with some data and make some predictions. But I mentioned previously a part of our history called AI winter that didn't have any big improvements in this area for a long time, and that's why it's called AI winter. And main thing why we didn't have any big improvements, big moves, is because we lack data. Now we have a lot of data, and one area of data science that is working with big data sets, terabytes, even petabytes of data, is called big data, and that's why we have this diagram here as a part of machine learning, because we are working with very big data sets, using those data to make some predictions. And technology part comes from the server side, the GPUs, and all other driving forces that comes from the hardware world. Cool. So somebody before mentioned regression. Now we are moving to the part of what actually we have as a part of as a type of machine learning. The first part is called classification. Really common part, you will see it everywhere. And that's basically telling us, okay, so yes, we have one class and the other. What is the difference between these two classes? And that's called classification. So we had our quick draw example where we had maybe 50 different classes. In that case, we wanted to distinguish each drawing from those 50 different classes and say, okay, this current image is the closest, or it is representing our candle. I think, yes, it was the example. So that's classification, really simple and most present in the current world. Then previously mentioned the regression. So regression is really useful. It comes from statistics. There are so many algorithms that are not considered to be machine learning that can be used. So we have a question, what are you talking about? I'm not sure whether or not I was lost, or did you miss one part of the talk? I'll continue with regression, and please write a question. Write your question in the chat. So yes, regression was or is part of machine learning where you are not predicting a class, let's say a cat or a dog, but you're predicting a real number. So in a sense of our house prices, we want to predict a real house price. So we want to say, okay, this house with all these features, such as number of bedrooms, such as number of bathrooms, square footage, all other extra things, is considered to cost, let's say, $100,000 or something like that. So that's what regression is. And in the example below, you can see that regression can be also used to estimate the time between 2 points. Maybe the exact the distance between those 2 points as well. So everything that is explained as a real number is considered to be a regression. We have another question. Can we say data is digital DNA? Yeah, it's an interesting question. I don't know how to answer on that. Sorry. Sometimes yes. So for companies, if you have pretty like unique data sets or something that represents your business, it definitely is something that distinguishes you from others. So in that sense, it is your DNA. But in general, it really depends on the type of data. So not all data is a quality data. I would say something like that. Share some talk about the its effect on the Middle East. Okay, so I really don't know about that. I know a few examples that did have influence on the Middle East. I don't know the exact country where it happened, but I know like the part of face recognition system did not work because of faces for, I think, babies were included in that. Then I think for LGBT community, it was a problem. Like some guy from, I think, Israel, I don't know, some team, sorry, from Israel created an algorithm to classify you as a straight or gay person based on your face. And that was a big problem with that, because there are so many people recognized as a gay and they were not. So yeah, that was a big problem, a big issue, and I think there was some lawsuits about that. And I think, yeah, it is a negative effect. For positive effects, like if you have a global application, it is influenced for the Middle East as well. But I would suggest contacting somebody from Middle East to tell you more about that, because as I said, I don't really have an idea what is exactly there. We have one more question from Richard. What is the key difference between programming language and GPU? Because mostly we care about the efficiency of the language and got education the way okay, cool. So yeah, so GPU is a hardware that you use to run your algorithms, and it is not essential. So you can run on CPU as well. There is one new type of processing unit called TPU, which stands for Tensor Processing Unit, developed by Google. So it is specifically optimized to work only for, well, not only, but the best for neural networks. And I would say, like, you can optimize your program as much as you want, but if you don't have enough power resources, such as like enough GPU power or even RAM sometimes to store your old data, it is like it cannot be that efficient. So combining those two, good programming with good hardware, is the best fit. And you should care about both. So good engineering is really cool to have in a team when you're working with some machine learning project some machine learning project. And yes, optimizing that to work on GPU is big advantage. Then we have clustering. So now all the examples. Oh, by the way, thank you all for the questions. Amazing questions so far. Now we had the examples of having some data and having some label or saying exactly what the data should be. So if we gave a house description, we already had a price in mind what we wanted to have, in the training set. We don't essentially have that information in a testing set, but you want to have that in the training set for sure. And in the classification as well. So if you have a cat image, you want to say your algorithm, okay, this is a cat, So clustering is a bit different. You have data, but you don't have labels at all. So how our algorithms should learn this? Well, it comes really to searching patterns that repeats throughout the data. So you have underlying structures that we as humans really can't see. So we go in the direction and saying, okay, this is the data, and this is something you should find. Like there is no exact idea what they should find, but find something. So if we give a customer data, for example, they can group the customer by age, by expenses, by average salary, by gender, whatever. There are so many different things they can use, or when I say they, machine learning algorithms can use to classify or cluster our data. So that's the clustering part. Sequence prediction. So I noticed that we are running out of time, so I will speed up through these few examples at the end so we can have a time for a few more questions. So sequence predictions is basically predicting what is the next in the sequence really easily. So in the sense, in the example here, you can predict what is the next character you want to have in your word, and that is like completion. So in that case, you can use the sequence prediction for predicting what is the stock market price for tomorrow based on previous 3-4 days. You can predict the temperature and many more things. So that is a sequence prediction. Style transfer. So for me, before looking at this presentation, I didn't want to consider style transfer to be as a separate like way of solving things, but it really makes sense, and I will explain in a second. So style transfer comes for when you have two different sources of data. They can be same, they can be totally different, and you want to produce like a combination of those two to make some prediction. So in the example above, you have a picture of a turtle and some painting, and when you combine these two, you get picture of turtle with that style, and that is original style transfer paper that describes like combining two images. In the example below, you have like a male and like female speaker that is in English and Japanese male. So you can combine all these three to produce like a third sound that sounds like a male Japanese speaker that has like a female voice, something like that. So you can combine different things. And when we speak about applications, so translating language can be considered as a style transfer because you are transferring basically from English to German language, so those can be considered as a style transfer as well. So this part of presentation is going through different examples of like applications of machine learning and what are they considered to be, like all these types that we considered. But because of time, I will not go into details right now of this, and I'll jump straight to the questions. So Richard told it's looking like a DALL-E. Okay, so did you mean about the artist DALL-E or about the model, recent model produced by OpenAI called DALL-E? So yeah.
Hello, Luca.
Hello.
It was a great section. Thank you very much.
Yeah, you're welcome. Thank you for calling me. And yeah, Richard told OpenAI DALL-E. Yeah, so DALL-E is working a bit differently, and the amazing thing about DALL-E is it is able to produce these types of arts, even though it's not trained specifically for that. So this is amazing, like thing that we can have right now these days. A few words about federated learning. So yes, so federated learning is a bit of advanced technique to outsource training of your models to basically multiple devices, and then you combine them to one powerful model, if I understand that correctly, yes. So I never done that in my career, so this is, as I said, a bit advanced, yeah.
There was a question during session. Let me read it. Luca, is it okay?
Yeah.
Can you hear me, Luca?
Yeah, I can.
can machine learning can create their own ecosystem with each other, with collect data and analyze from network? You can think that like self-learning and can themselves?
So, yeah. For now, we didn't see that. Okay, so that is a bit of a lie, and I would say why. We saw a bit of algorithms talking to each other from Facebook a few years back when two algorithms created their own language and communicated between them, and nobody understood what they were talking about. So it was kind of scary moment because it went kind of alive, which we don't want algorithms to do without our control. So in that sense, they can go and create something, but code for themselves, for now, no. Unfortunately, it would be amazing if we can tell something to an algorithm and let's make another application and basically do that. For ecosystems, so you can consider to have like reinforcement learning create their own ecosystems inside their own algorithms. So that can happen. And we saw that from OpenAI, like hide and seek, where they learned a lot of patterns without explicitly telling them to. And in that sense, we can expect something to emerge from behavior, but not exactly to have consciousness. So no robots won't kill us anytime soon. But
I think questions are done.
There is one more, I think, from Yunus. Can machine learning create their... Oh, no, that is the same question. Okay. So, just repeat it.
Okay,
if you have another question, you can write chat part.
Sorry?
Yeah, there is no question, I guess.
Okay, cool. So, thank you very much for being here with me, guys, today.
We thank you, Luca. It was a great experience for us.
Yeah, for me either. Thank you very much. Enjoy the rest of the summit. There will be amazing talks. And if you want to connect with me, please reach out to LinkedIn. I'll be happy to answer any questions that you didn't have time to ask during this session.
I think one more question. Do you have time, Luca?
Yeah, of course. Yeah.
Do you have any recommendation for technologies to use when working on machine learning models?
Mm-hmm. So if you mean by technologies by like programming languages type of or environments when using that, it really depends on the programming language and the company that you work in. So sometimes it can go like I say so. Jupyter Notebook is amazing for experimenting. Python itself is cool for programming it. There are some like great AutoML platforms in Google that will find algorithms for you and help you find the optimal algorithm for your data. There are libraries, a lot of libraries right now that will optimize your algorithm and find the optimal like structure of neural network. And potentially, like next speaker will talk about that. So you will have that information as well. So there are many things. For recommendation, I will need to think really about it and then recommend it. So please reach out on LinkedIn and I'll send you.
Okay. I think there's a problem about the form. If it is not still open, we will fix it and send it through the chat one more time. It's not a big problem. And I think we are done, Luca.
Okay, cool. Thank you very much and see you around. Enjoy the rest of the session.
Thank you.
Bye.
Thank you very much. See you.
Thank you for presentation.
Thank you. Bye.
Guys, we will give a 2-minute break and after that we will continue. And during that time we will try to fix the issue.
Hi everyone. We will start neural network part. Guan Wang is here. Welcome, Guan Wang. Thank you for accepting our invitation. Can you briefly introduce yourself?
Sure. Thanks for having me here. Actually, just before this session, because I'm actually a machine learning Google developer expert, and we were asked to actually create a video to introduce ourselves, and it's all on the MLGD YouTube channel. Maybe I can already share the video here. Just give me a sec.
Could you please give some detail about presentation?
Sure. So this I will cover the neural networks, and it will be the basic concept, and I will try to cover hands-on style so that we actually go to a lot of several exercises.
Well, I think there's a problem about your connection. Do you have no problem, Victor? Is it only for me?
No, there's a problem.
Hello.
One, you are lagging, and we cannot hear you. Okay, it's okay right now, I guess.
So can you hear me and can you see the screen? Sorry.
Yeah, we can hear you.
Yes.
Right now.
So let me play the video just as a self-introduction. Can you hear the sound, by the way?
No.
Not now.
Let me try again. Because we will be using the screen sharing quite a lot, neural networks in content. So I just want to make sure everything works. Can you see the screen now?
Are you sharing?
Yes.
Let's add to stream. Could you please play one more time? Yeah, we can hear. We can hear right now. Yeah, it's okay.
Right. So let me share our presentation for today.
We go backstage. You can start section.
Sorry?
We are leaving now. If you are ready, we will be in the backstage.
Yes. So today we'll be covering about neural networks. Let me know if you can see the screen and the slide deck. So before I go into the content, maybe just a recap of myself, right? So I'm currently a senior data scientist working at Swiss Re, a Swiss reinsurance company. So I'm actually in the insurance or in the financial domain. But I've been working in machine learning and also in all these applications of AI for quite several years. And I'm also a Google developer expert, so machine learning Google expert. So trying to give you a good idea of what neural networks is like today. I will be using actually a nice slide deck made from Google covering the neural networks. So at the start, let me just share this video with you again. Bear with me.
Juan, we can't hear you right now.
Not even all the video.
Can you hear the sound of the
We
video?
can hear you, but we cannot hear the sound.
Right. Let me share again. Can you see the screen?
Hi, I'm
And
Nat.
can you hear the
Hello.
sound
And
now?
This is our 20% project, where we go find out about different Google stuff we're curious about.
Yeah, it's all
Last
perfect
year,
now, Glenn.
Documentary about how voice search works. And that was the first time we heard about something called machine learning. Since then, we've been kind of fascinated by it. So today we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems it's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it. But for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters.
When you go to the ATM and you give a check and it can read the handwriting.
Or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos.
Here are all my dog photos.
Here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in a particular collision at the LHC.
Which we would just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this. Ooh. Ooh.
So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal that's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high-dimensional knot and pull it apart and make it easier to go and separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll put two neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, oh, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog.
And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything it can classify as? And suddenly you can go and ask, neural net, what do you think cat looks like? And you get a picture of a cat. Or, neural net, what do you think a barbell looks like? So these weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, it only learned what barbells were from looking at pictures of barbells, and they're often held by muscular weightlifters. And so it learned that there was, barbells have arms attached to them.
It takes them a long time to learn. You show it a picture of a school bus when it's early in learning. The very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, say to a kid, that's a filing cabinet. And then a second later you say, what's that? Yeah. He's not going to be like, shoe, right?
Well, like, the more you describe this, the more I'm amazed by human beings.
Yeah.
The effect is like, wow, human beings are really amazing.
We're really amazing learning machines.
All right. So what is a neural network, right? Probably you've seen this kind of similar structures before, that the neural networks are a lot of neurons and a lot of layers of neurons. But how does it work, right? How does a neural network really work? And by the way, before everything, right, when we talk about neural networks, we mean the artificial neural networks. We don't mean the real the neural networks that is in our brain. Even that this artificial neural network is inspired by the real neurons, where you have neurons, you have the electric signal that you activate a neuron. So the concept is similar, but it doesn't really mean that this artificial neural network is what we have in our brain. In our brain, it will be way more complicated, I'm sure, but this is just an artificial one. But I think probably in the previous session in machine learning, you've also got some of the basic concepts, like what is the training data, and what is the label data, and what is the training process of a model is like. So in this example, as you can see, there are some labeled photos of cats and dogs, and those are pictures, right? Those are the pictures. When the computer actually sees it, it's actually just a bunch of pixels. If you think about some traditional machine learning methods like linear regression, logistic regression, or even a decision tree, it's kind of really challenging for you to develop these kind of algorithms to tell if a picture is a cat or a dog. There are traditional computer vision methods trying to do that, which basically generates or mostly manually generates all these features, like there's a curve somewhere, you do dilation, you do all that different kind of traditional CV methods, and you get features like curves, like a circle or triangle and something, and you try to use that features to train a machine learning model to get the results. But those methods were proved to be not so efficient. And what neural networks are amazing is that they're really, really good at this, what we call the cognitive tasks. Like, can you tell from the pictures if it's a cat or a dog or something else? Or can you tell, if we're talking about natural language processing, can you tell if this piece of news is talking about sports or politics or some other themes? And again, if you think about texts, if you think about natural language processing, how can you actually do it with traditional machine learning methods? There are indeed traditional machine learning methods with manually generated features like bag of words, like all these the distance between certain keywords, all that manually generated features, you can feed them into a traditional machine learning model and generate results. But those were proved not to be so efficient. And people will really find this problem challenging until that we find this kind of neural network structure that works pretty well. And by the way, the neural network has a very long history in the research world. It's not that only recent years we've come with neural networks. It's only because one of the reasons is because we have way more computational resource now. Because as you can see, for a lot of the challenge problems, you will have millions of neurons, hundreds of layers, and all those things will need a lot of computational power. And it is only because the recent advance in this more computational power that we are allowed to train this kind of neural networks. And then it is proved to be quite efficiency. So what are neural networks? A neural network, a trained neural network, you can just consider it the same as all the traditional machine learning functions, right? It's just a function that maps the input data, the input features, the dimensions, different dimensions of features we call x, the different x1, x2, xn, to a target function, to a target variable, which is y. So in this case, the x will actually just be the pixels of the picture of cats and dogs, and you input into this gigantic function, and you output just a label if it is a cat or a dog. And same as traditional machine learning methods, you also need to first train the neural networks. The way you actually train it is that you input you have a lot of label data. So all these pictures are already manually labeled, probably from I don't know, Instagram or something, because when you upload a picture, you normally have a tag on it. So big companies will just use all these tags as their label data and use those tags as the labels of the pictures. And you just input all these labeled pictures, the training data, into this kind of neural networks. So it will initially it will just all be random weights between the neurons. The neurons status will all be randomized. But since you have the label here, so if it gives you a correct label, then it's a correct prediction. But if it gives you a wrong label, it will give you some error. And you will need to do something like backpropagation to actually update all these weights on the connections between the neurons to actually update those weights so that you have more and more pictures. You have like millions of different pictures. All these weights are optimized for this specific task. So eventually you trained a magic neural network that can tell you if it is a cat or a dog. So let's go a bit more into the details. What are the neurons and what are the links, right? So a neuron is what we think is basically just an activation function. So we just apply activation function to one of the neurons. You have an input into this activation function. And this activation function will tell you, okay, yes, the input actually goes beyond the threshold, so we need to activate that neuron. And if it doesn't, then we do not activate the neuron. So this is almost very similar to if-then statements. But you will see that it is a bit more than that, because this activation function, we can actually introduce something like nonlinearity so that it can imitate. So one activation function is a simple function, but you can imagine with a lot of links, a lot of neurons, it can try to imitate any kind of function that we have, including from cats and dogs to the label, from pictures of cats and dogs to the label. So we hope that a lot of these neurons together as a whole will try to achieve that. So I give you an example, right? So the simplest one is just the activation function is that this is smaller than 10. So if you have an input as 5, it will show that, okay, yes, it is smaller than 10. So it will go on and activate the neuron. You will see what activate neuron means. But this is just the simplest version of the neural network, right? And it is just more or less like a linear regression because it's just a less than a very simple logic here. But what if it is a picture? So if you consider, like I said, a picture is just a bunch of pixels, right? So this is a picture of a digit 7. And you come to this activation function, and it basically asks, does it has a curve in it? A curve will be something like a C, right? But this is only half of that C, correct? The alphabet C. So it does not have a curve. So no, we will not activate the neuron. So this input will not activate the neuron. However, if you have another picture like 6, you will see that it actually has a lot of curves. Right? It has a curve here on the upper part of it. It has multiple curves in the lower part of that picture. So it does has multiple curves. So yes, it can actually activate the neuron. So this activation function can check actually if you have a curve or not within the picture. Now there are some common activation functions, and as I said, probably if you compare a machine learning algorithm to a rule-based system, right? If you're just writing some rules to map some functions, you will need a lot of domain expertise. One of the example would be that because I'm working in the insurance industry, we have a lot of underwriters trying to decide if you are a good health or good risk, health risk or a bad health risk, because it will depend on whether we can give you an insurance policy or not. And traditionally, it will be a large rule-based system where the underwriters will write, okay, your BMI has to be lower than something, your age has to be in what kind of a range, your blood pressure, your all that health records needs to be within the range. So you can have all these kinds of a rule-based system. However, all these concepts are actually changed or switched to a data-driven approach here in machine learning algorithm, including deep learning, deep neural networks or deep learning. And that is that you have this system, you have a lot of data, you feed the data into the model, and the model will try to learn the patterns within the data to give you the target function. However, what off patterns are within the data, that is actually a very important part of the model, because normally if you have a very large neural networks, people will consider it as a black box. And it is a very big question, how can we interpret this kind of black box models, especially for traditional industries like insurance or banks. If the underwriting decision system is actually giving you results that you are not fit for an insurance policy, then you will probably ask why. And it will be a challenge for neural networks because what you get is just a bunch of this one. And how can we explain to the policyholder that, okay, it's you're actually rejected? If it's a traditional rule-based system, probably can tell you, okay, your BMI is a bit too high, or you're just too old to get a normal insurance. You need to pay more premium on that. But if it is a neural network, how can you explain it? And normally people don't really think about it, right? Because if it has a cat or a dog, as a human being, you can easily tell, right? This is obviously a cat. This is a dog. But why? Why is this a cat? Why is this a dog? They all have that curved ears. They all have eyes and mouth and even similar color with each other. How can we actually tell, right? So this, I mean, as human ourselves, we can't really have a very clear explanation on the results. And that's the same challenge actually applies to things like neural networks. And with that, actually, a lot of the deep learning research are in the recent years are more empirical than theoretical. Meaning that when you do research in deep learning, when you find a certain neural network structure actually works better than others, when you find that for certain tasks, actually one kind of neural network structure works better than others, or like recently we just trained very large neural networks like GPT-3 or BERT, And it kind of works well for all the different NLP tasks or even the computer vision tasks. Why is that? People, when you look at the research papers, there are a lot of empirical explanations. But I would say, because my major, when I was in university, I studied physics, but none of them actually gives you this kind of exact mathematical explanation why it works that well. And it is not really based from like first principles that you derive all the explanations. Instead, it's just more as a data-driven trend model, and it's more empirical. And sorry for the long background explanation, but that actually brings to these activation functions. This is definitely not the only and the to-go activation functions. Actually, in history, people also have a lot of other activation functions like tangent, arctangent, all that. And this is, people tend to use sigmoid for a very long time, which you can see is a curve of this one. But only, I think, recently people find that even a simpler activation function like a ReLU, which the curve is like this one, will actually be more efficient in computation. As you can see here, you have a more complicated computational here, but this is actually much simpler to compute, and it proves to be even more effective. It means it actually works better in a lot of the scenarios. Why is that? Again, there are a lot of empirical explanations behind it, and people try to really to prove it mathematically. But again, I think all this whole development of deep learning, of all these deep neural networks, is more like experimental science instead of theoretical science. That's what I feel. So again, coming back to the question, right? If you have a picture, you want to prove, you want to predict what kind of what is in that picture, and you see that there's a Labrador here, a dog here, and there's a cat here as well. So how can we actually? So the first question is, with this neural network, how can we explain it? How can we? How do we know what is happening behind the neural network, the layers, the neurons? What is happening here, so that it actually decides on the label of the picture? There are a lot of efforts in this, and one, I would say there are several methods. One method is actually it's more as model agnostic, and it's only try to look at the final results and give you some kind of a feature importance, and that will be something like the thickness of this links. So it gives you, okay, this output of the neuron actually gives a higher contribution to the final label. And of course, within the neurons, it will also give you, okay, this kind of thicker links, meaning it gives you a bigger contribution so that you can decide the final label. But also you can look at the neurons. And what the neurons does is that normally when you have this kind of pictures, it will go through a convolutional neural network. We won't even cover the definition of convolutional neural network, but basically it will do a lot of different transformations along the pixels, and it will do convolutions on the pixels with the pixels around it. So it will generate a lot of strange and colorful pictures that tends to only appear in our dreams. And you can see that that's also an imitation to your brain, right? When we sleep, when we dream, probably we're going through some similar stuff like this, so that we learn things, especially for the young kids. But when you look at the neurons, they actually can be visualized. What kind of pictures, what kind of features from that pictures, or what kind of results from that kind of transformation are in each of the neuron. And as you can see, there are a lot of different distortions and different curves, combination of different shapes, so that it finally gives you a result here. As you can see, there are weights on the links, and there are also the activation function, and there are also bias on the links. So when you have a lot of pictures like this, it will basically train a neural network. So each of the link will have a finalized weights. And when you do the inference, you just input a new picture. It goes through all this forward propagation of the weights of the signal, and it will give you a probability of each of the labels, and you just choose the highest probability as the label. But of course, there are possibility that all these labels have very low confidence score. Then probably it's others, right? The model can't really tell what it is in the picture. And again, I mean, this is a simple problems, but if you think about it, now we have a lot of much more complicated tasks, like not only telling cats and dogs from the pictures, but if you think about, for example, the self-driving cars, especially if you're using cameras, then it will be 2D information. So 2D information basically covers the pixels and the position of the pixels. And each of the pixel will have RGB 3 colors. So the 3 channels of numerical pixel intensity in that picture. And if you think self-driving cars, it will use this kind of picture to tell if there's a car behind, in front of you, if there's a tree on the side of the road, if there's someone riding bicycle along you, if you're in lane when you're driving. So all this kind of information needs to be investigated through a sophisticated self-driving car algorithm. And you can consider each of that subtask might be just a problem like this one. You have to tell if it's you have to tell what kind of object it is. And this is only for pictures. But if you think about, for example, natural language processing, you think of chatbots, so that you input some text and it will give you an answer in natural language. All these NLP tasks can also be achieved or can also be tackled by this kind of neural networks, but of course with different structures. Like I said, normally for computer vision problems, you use convolutional neural networks because it can handle this, can handle the position or can handle the spatial information of the pixels. But if you have a time series data, like stock market data, or if you think of natural language processing, you think of sentences, they're basically sequences of words, right? So these kind of problems are normally tackled by sequential models. And traditionally, it can be Markov models, it can be, but here in the neural network context, we normally use the simplest one will be the recurrent neural network. And then with that, we developed something like LSTM, or recently we actually used something called transformer to handle this kind of NLP problems. So with all that, that's maybe just way too complicated for you. So I actually want to come back to a nice toolset, which is developed by Google and with TensorFlow. It's actually a playground where you can play by yourself. It's called TF Playground. And basically, if you're really new to machine learning, to TensorFlow, and you don't really know how to code at this moment, you don't really know Python, then this kind of dashboard will be a great place for you to understand the concepts of machine learning. But gradually, when you pick up the concepts, you can already try to use some of the existing packages like TensorFlow to create some of your first neural networks. Again, when you think of TensorFlow, you may think it's a very complicated, large software package, but actually it can be really deep. But as a new learner, as a green hand, you can already just use its very simple APIs or some of its very simple functions to actually just create your first neural network. And it's actually very intuitive, right? It's basically just several neurons and several links on that. And we will not cover the coding in this session, but if you've got a chance, please try to check some of the tutorials for introduction to TensorFlow, and you can already create your new neuron and your new neural networks with your neurons. But of course, if you've played with TensorFlow for some time and you find that this is really interesting, I want to know what's happening behind, then you can first read some of the papers. Actually, again, if you think of academic papers, you might think it's too deep, a lot of mathematical formulations, all that. But one thing I really enjoy when I read an academic paper is actually to read its abstract and also its introduction. Normally, there won't be too much mathematical formulation in those parts, and it gives you a really good overview on the background and the context of what it is trying to solve. So the academic papers can be a good place to go. And then another one is, of course, to look at the source code. Amazing thing about machine learning community, especially in the Python community, is that people love open source. There's a huge open source community here to actually contribute. And you can see that TensorFlow itself is open sourced. Of course, now it's TensorFlow 2.0 plus already. But if you're interested, you can, if you're already played around with TensorFlow for some time, you can definitely go check the repo on GitHub. And for some specific functions that you use a lot, you can try to see what's happening behind. It will be some great learnings because all this code are written by some really great people. The code, the style of the code, the format of the code are excellent. It's a great learning for you to actually learn a bit how to code, what should be the formats. And even that you find, okay, I want to do something, but the TensorFlow still doesn't support, or I actually found a bug. I tried to raise it in the GitHub and people can't really solve it. Then probably you can even contribute code to TensorFlow, and you will be a contributor to TensorFlow, and probably you can get something like a hat like this one, and they will award you with some like these gadgets with TensorFlow. But it's really, really a nice community. So on that, this dashboard is actually based on TensorFlow, and it's called TF Playground. Probably the link will be shared to you on this playground, but I can just walk you through quickly what they are, right? So on the right-hand side, you will actually have some of the data points. So different color will be the different labels of the data points. As you can see here, we're trying to distinguish two different kind of data points. One is on the circle around it. Another are several points inside it. And you want to find a classification model, right? You want to find a boundary that you can separate these two kind of points, the dots. So how can you do that, right? If you think of only a linear model, you can't really do that. You can't really separate these two kind of data points by just a line, right? You can't really do that. What you can do is probably to draw a circle here, so that you can separate it. But as you can see, this is a non-linear problem. It's this circle will have non-linearity inside of it. So it's a great example of it's very essential to have non-linearity in your model. So this is what's on the right-hand side of the dashboard. And you can also see in the background a bit of the color, and these are actually the color of your model. So if you have a classification model, you can see this is really not a good classifier, as you can see, because it's still quite linear and it kind of put the wrong color into the regions. It can't really tell if the pictures are there. Then on the left-hand side, these are the features. So you can see for this playground, it gives you like x1, x2, the horizontal and vertical line. It also gives you like x1 square, x1, x2, sine x1, sine x2. So the raw data are probably just x1 and x2, right? But if you have a really complicated neural network, probably it can help you already within some of the layers to help you generate features like x1 square or x1, x2 to try to imitate all these kind of features. But you will see that feature engineering is still super, super important actually for deep learning or for neural network algorithms. So if you do know that, if you look at the picture, you do know that, probably there will be some nonlinearity on the boundary here. So you probably want to add in some of the nonlinearity, some of the functions, the new created features here, so that it will help facilitate this neural network quite a lot to actually get the correct separation boundary. But of course, these features are x1, x2, but in different scenarios, you will definitely have different kind of features, right? Some examples, like if you think of dog and cat, it can be the size of the animal, the color of the animal, even the length of the tail. If you're thinking about classifying some characters, especially if you're talking about Chinese characters. How can you tell from the thousands of Chinese characters what character it is from a picture? Then it can be the number of curves, the number of lines, the thickness of the different part of that character. That may all help. And of course, you can even use this neural network to, if you've been to Kaggle before, if you've tried with your first machine learning project, probably it can be the predicting the housing pricing, right? The house pricing, to predict the house pricing with, for example, the number of bedrooms, the location of the house, or the size, the square meters of the house. So all these are features. And let's just talk about the square meters, right? I mean, you can totally just put the number of rooms, the location as part of the feature, and you can just put, I don't know, maybe the length of the length of the room and the width of the room as the features. But you will hope that it can be enough. But actually, you know that a very important feature for the housing pricing will actually be the square meters, which will be the multiplication of the length and width. So if you have this prior knowledge, then it will be great if you can just manually generate this kind of prior knowledge into a new feature, the square meters, and probably it can facilitate the model already a lot. This part is the features. And then we come to the neural network part, right? This is where you can, without writing any code, you can already try to generate your own neural network structures, the different layers, in each of the layer, how many neurons you have. But of course, this is just very simple structures. And you will see that maximum it can let you create perhaps 6 layers of neurons. Each of the layer you can have maximum 8 neurons. But in reality, you can have hundreds or thousands of layers. And within the layers, within different layers, you can have new links that cross from different layers. So here you're only allowed to link neurons from adjacent layers. You can only link from one to one that is next to it. But in reality, I always say that building neural networks is very much like building Legos, right? You can just build whatever you want. And in reality, you can even have what we call the highway links, so that you can link one layer of neuron to some neurons way deeper into the structure. And you will see that, before people tend to play around with all these structures, but recently we've come with more complicated structures like transformers from BERT and GPT-3. They are all using the structure called transformers. And it's kind of already dominates our world, at least in the deep learning world, just like in the movies, right? The transformers are dominating. But it turns out that these kind of structures that people are still experimenting a lot to finally get these kind of structures. Why? What is the mathematical formulation? Do people get it from first principles? No. Probably it's because of after a lot of experimentation that people find this kind of structure actually works pretty well. And it proves that it's working not only from the natural language processing that it first came out with BERT, but recently we find it also works very well for computer vision tasks as well. And you will see that, as I said, all this TensorFlow, everything is open sourced. So it's quite what we call the democracy of the AI, so that everyone, you do not need to be working for Google, you don't need to be working for Microsoft. You can just git clone the models and git clone the code onto your own computer, and you can already create your own model. And you will see that even you don't have a powerful computer with this kind of web-based tool set, you can also do that just in a web browser. But what makes me a bit concerned actually is the recent development of all these very big models. It first started with the computer vision models, where you have the ImageNet and you have other pictures that you actually people, especially the big companies, they actually trained huge models. And then when you have a new task, for example, you want to apply it to tell cats and dogs, you just need to what we call the transfer learning, right? You just need to use the existing model parameters, the huge model, and you only have to fine tune the last layer of the neurons and all these weights. So the previous like hundreds of thousands of layers, the parameters on the links, you don't really need to change. You can freeze it, and you just input a few more examples of cats and dogs. You just retrain the final layer. It will work very well. So it started with computer vision, and then it came to NLP, to natural language processing, dealing with texts. And people tend to find that structures like BERT, which is trained with huge corpus, probably the whole dump of Wikipedia page, plus some of the news, a lot of the news texts, and people actually train huge BERT models. And recently the GPT-2 from OpenAI, and recently the GPT-3. By the way, GPT-3 is not even open source, because I think OpenAI people, they think if they open source, some bad people might use it to actually, I don't know, destroy the human being or make it to harm people. But you can try to apply for a trial on their API, and you can find that it's really amazing that you can input a picture. You can input a picture and let it to describe what's in the picture. You can input a sentence, and it will basically tell your story based on that sentence. So all these amazing things can be done by a GPT-3. So it's more like even like artificial general intelligence. But if you really dig deeper into that, you will find it's actually not perfect. I did some experiments, like if you input like a white man it will probably tell you it's a pilot, it's a white collar worker or something. And if you input like a black woman, and then it will probably tell you she's working as a janitor or working in a restaurant. So it definitely have all this bias, all this even what we call discrimination or imperfect stuff trained within the model. But that is unsurprising, right? Because in real world, if you look at Twitter, if you look at all the real world data, the real world data is in bias. That's why the model that is trained from this real world data is biased as well. So that's something about neural networks. But I think I can already try to guide you through some of this playground. So let me reshare my screen. Can you see the screen? Yes. Yes. So probably the link will be shared to you, or it's already shared to you. So it's just like I said, it's a playground that you can play around. You can input different neurons. You can change the parameters. You can change the learning rate. The learning rate is basically how fast you want to change your how much you want to change your parameter with each of the error coming in. If you put it to a large number, it means that you will change a lot according to the direction of that error, but it will probably give you to an overfitting situation. But if you choose it to be very small, it means that you will just fine tune a little bit with each of the error. It will probably avoid the overfitting situation, but it will also mean that you're doing this training in a very slow manner. So you will probably need to wait for a much longer time before you can get the results. Activation function, you can have a linear activation, you can try, but of course you can have sigmoid, tangent, and also ReLU here, and ReLU is what we recommend. Regularization, you can have no regularization, but you also can have L1 and L2. So L1 regularization means that you just use the absolute value of the weights as a regularization, and it will tend to move you towards the median of the data points. A good thing about it is that if you train the model with L1 regularization, some of the features, the weights of that features will tend to decrease to 0. So it's a good technology for you to do feature selection. But if you change to L2, it's basically try to give you the square of the weights as a regularization item. And if you use that, it tends to give the not so important features to a very small number. So you can't really do feature selection with it, but still L2 is, I think, computationally it's more efficient than L1, and you can choose the regularization rate here. So now let's just try with our first model. You can see that we have two features, x1 and x2, and you have just one neuron. Remember, each time you have to restart here, and you can see already. So before training, you have the random parameters here. You can see the model can already give you a classification of course, it's a random guess with this boundary. And you can see, so this is the real data points, and you can see the background color is a result from the model, and you can see it's not so accurate because it's random after all. So you can run it. You probably can see the test loss and the training loss. So the training loss is that when you click it, it will train the model and apply the model to the training data and get a loss here. Of course, it will be some number that is decreasing along the way because it tries to use the error to improve the weights on the links so that it kind of give you less error. You also have a test loss. So here you can see that you can also show the test data. So the test data will not be used during the training process. It will only be used for the testing purpose. So if it is overfitting, the train loss will continue to decrease, but the test loss will actually start to increase because it's overfitting. It fits just too much to the training part of the data, but it kind of loses its generalization capability, so it gives you worse result on the testing data. But here, as you can see, if we continue run it, the loss are huge, right? As you can see from the background, it's not making really a really good classification on that. That is probably because we're using the linear model here, right? Because this neuron is actually a linear activation function, and we're using the linear model. So it can't, as you can see the data, you have the blue data here, you have the orange data on the other diagonal of this. So it's kind of, you have this kind of nonlinearity within it. If you're just using a single line to try to separate them, it's not that feasible. So how about let's try to, so this is what we call the underfit, because it can't really fit the data. So let's try to use let's try to use ReLU, which we hope it will create some nonlinearity. But also this is just one neuron. Let's create a new neuron here so that we actually have two different kind of neurons here. Let's train it again. You can see previously it was 0.5 for the linear model. Now we can see it's already improves quite a lot, 0.3. And by the way, under the hood, this is all, I believe it is all done on Google Cloud, somewhere on Google Cloud to try to help you do all this training. You don't even need to have a computational, really powerful computer to actually run this. It's just a web page that everyone can run. You can even run on your iPad or your mobile phone. So let's see. So we have two neurons, and with just one layer, it seems that the results, so we continue to train it. It seems the results is better, right? You can already see this separation, but however, you can't really have the lower bound of this data. It can't really, still underfits the data itself. And by the way, let's run it again, and you will see the result will be different because this is non-deterministic. It means that there will be some stochastic process within it. There will be some random number within it. So with a different initial parameter settings with some different randomized weights, it will actually give you different results along the way. But still, I mean, this is actually a much better result already. You see, even with this kind of separation, the loss is already quite low. The green and the orange dots are quite nicely separated. But as you can see, it's still underfit, right? The loss is still quite large. So how about we add a new layer here, and let's see. Let's create two neurons. Let's run it. Now, as you can see, since our model is more complex, you actually have quite a big difference between training loss and test loss. And you can see the test data here. these are the training data. It means that the model kind of fits okay on the training loss, but on the test data, it's actually not that good. And probably you will even, I mean, in some other structure, we'll see that the training loss is stable, but then the test loss starts to increase. It means that it's really overfitting on the training loss. But since we are using a very simple model, overfitting is really not likely to happen. So now let's try to do something, right? Let's try to have 3 neurons on the first layer. Let's try to have the 3 neurons on the second layer, and we even have a third layer with 2 neurons. And let's just play around, try to run it. Let's put even a higher learning rate so it can fit faster. You can see it gradually captures the structure, the boundary, as you can see. And the training loss is quite low here. It means this kind of more layers of neurons with more neurons within each layer, it can actually give you already a pretty good result here for the separation results. So there are actually 4 tasks here. I mean, if you have the link and you can run it, you can probably just play around with it according to the task and get even more sense on how this works. But let's come to the second problem, which is the neural net initialization. Again, this part you have the same training task, right? But you want to still want to do this, but the task is that let's try to see if this model can actually give you consistent results for each run. Let's run first. It gives you, as you can see, this kind of boundaries. So this is green, this is blue, this is orange, and of course it's not perfect. But let's start again and run again. As you can see, it totally changed, right? Previously the boundary was here, but was on the left upper corner, but now the orange boundary are actually on the down right corner, of the bottom right corner. So basically it means, like I said, because there are a lot of randomized random process happening under the hood. So different, the random initialization of the parameters will actually tend to give you different results along the training process. What about, let's add more layers. So let's add 2 layers, and we try the same thing again. Let's see if what the result will be like. So add 2 layers. So this time is orange, orange, green, green. Let's restart. So it gives you a different results as expected. Now let's do it again. So I kind of hope that, let's probably add a new layer and try. Please, I mean, if you do also have this tab open, please just try together with me and let's see the results. I think the whole purpose is that with more complicated neural structures, you can actually try to get more and more complicated boundaries happening here. And you can, as you can see, actually for this one, we happen to get a good result. But it's not always the case, right? I mean, you see that previously I tried several times, it doesn't really give you such a good results on the goal. And that is the whole point, because training neural networks is experience plus luck, actually. So a lot of questions actually raised during the deep learning research that people find it really difficult to replicate what the researchers have achieved within their papers. And a lot of arguments, even quarrels are happening between the scientists or between the researchers. And when you develop some project, when you publish a paper, it's highly recommended that you not only publish the code, but also to set a fixed random seed so that you hope that people are easier to actually replicate your results instead of getting different results every time. I mean, if the readers get the readers of your paper gets lucky, you can get similar results of this one. But if you're unlucky, probably get something else, and they will okay, this one gets you the same result. And this is because we have a more complicated structure and it kind of more stable when you do the training. But if you have a less complicated structure, you will see that it depends a lot on the luck, whether you can replicate the results or not. So this is about neural net initialization. And then we come to very interesting data points, right? It's actually what do you call this? I call it a lollipop, right? It's like the candy that you eat when you're a kid. But this is totally, you see the blue dots and the orange dots, they're totally screwed up with each other. You have to really find all these very delicate boundaries for you to actually train this kind of a neural network. And you can see that in this playground, you're actually be provided with more features like the square, like the sign. But let's first try, right? Let's first try with just x1 and x2. Let's first try to see if we have a very complicated neural structure and see if it can, what kind of result it can get with just x1 and x2. As I see in this playground, you can have maximum 6 hidden layers. Within each layer, you can have 8 neurons. Let's run it. Oops! As you can already see, right at the start, the training loss is decreasing, while the test loss actually increase a bit. It means that within this part, probably it's overfitting on the training data, and the test data is actually giving you bigger loss. But then you see it comes back. Probably it starts to pick up some of the patterns here. But as you can see, it's very, very unstable. If you see the loss curve, I can continue to run. Very unstable here. It's kind of oscillating around. This is a very complicated structure. You can already see a bit of the patterns here, right, on the blue and the orange dots. But the curve is not that smooth. It's kind of artificial here, and it's, as you can see from the loss curve, it's not stable at all. And you can even see some of the features within each of the neuron, as you can see here. This is each of the neuron, because each of the neuron itself is also a classifier based on the previous inputs. So as you can see, each of the feature. But as you can see, since we only use the linear, the x1 and x2, it actually gives you some of the very sharp curves. However, if we, for example, put some nonlinearity here, still with the most complicated features, and let's put it to a smaller learning rate, so we try to fine tune it, and let's see what's happening. Wow, you see even the training loss is decreasing, the testing loss is increasing at first, meaning because this is so complicated, it's a powerful neural network, you have all these nice features, it's probably at the start will overfit will start to try to fit the training data quite it tends to fit the training data, so the testing loss is actually increasing, but later it kind of finds a pattern well, so both the loss will be decreasing, but still you find that it's very unstable. Finally, you have all this oscillation in the loss curve. So that is probably because this neural network structure is just too complicated. So let's see, we just have 3 layers. We decrease quite a lot. Let's have 4 here. Let's have 3 here. And let's have 2 here. So let's have a much simpler neural network, but still with all the features. Let's see what will happen. So you can see with a simpler neural network structure, it gives you actually even a bit smoother curves, but of course it's the fitting weight is the fitting curves are still oscillating here. So you may have the question, right? How can we train a neural network like this? For example, this one is totally a failure, right? The training loss is decreasing, but the test loss increase and oscillating in a very high point. This is probably a very typical example of overfitting. So you might have this question: how can we actually train a neural network? How can we choose the regularization? What is the regularization rate? How can I choose the activation function? What should the learning rate be, right? That's exactly why I said that training neural networks is more like experimentation instead of theoretical work. So you need to do this once and once again. You need to see the results, try with the different setups, and get more and more a better sense of what kind of structure or what kind of number of neurons kind of give you better results. So for that, I will actually try to play this video and let me reshare so to make sure that I have the sound okay, and we will so that we can see so we can see the video. And I think it's a good example of how you can actually train a neural network. What would be the experience behind it? Can you see the screen? I'm wondering if... Yes, let's play the video.
This is the MLCC neural net spiral exercise. So if we use the default parameters for the model, we can see that it really doesn't perform well. Even after 2,500 iterations, we can see that the test loss is still above 50%, and the model really isn't learning the data at all. So let's see if we can do better. Even though the data looks complex in this spiral, intertwined spirals, we don't need a super deep or complex model to solve the problem if we have the right features and the right parameters. I'm going to talk through a couple of pitfalls to keep in mind when solving problems like these. The first task asks us to train the model using only X1 and X2 without any additional feature engineering. So the first model I'll try is adding tons of layers and tons of neurons in each layer, because more is better, right? And so this is our first pitfall: too many nodes in the graph. This model is really slow because it's computationally expensive to adjust all the weights in the graph when you have so many nodes. You can see it counting through the iterations really slowly. And also the model is not very interpretable with so many layers and nodes in the graph. The first layer of the model sort of makes sense. It's these linear features at different angles. But as you get more into the middle of the graph, some of these features are not really clear how they contribute to the spiral data outcome. So you can see our test loss has improved. We're definitely below 50% now, but it's still not a very smooth curve. So let's see if we can reduce the number of nodes and see if we can get a faster model that makes more sense and adjust the parameters as well to get better test loss. So we now have 4 hidden layers in the graph with 20 total nodes, which is less than half of the 48 we had previously. It's still not a super simple network, but it's better. It'll train faster. And I'm also going to reduce the learning rate so that we don't get all of that jumping back and forth in the loss curve. Hopefully this will give us a smoother loss curve and not overfit to the test data. So let's see how this performs. With fewer nodes and a slower learning rate, you can see that the model is learning faster. The iterations are going much more quickly, but we're still getting similar test loss. But you can see that the loss curves are still oscillating and that the model output is much spikier and not as smooth as the spirals we're trying to fit. And that brings us to our next pitfall, which is no regularization. So regularization penalizes complex models and overfitting. So we can see if we add this if we end up getting a smoother loss curve and a better fitting model that's not trying to overfit to the training data. So let's add regularization to the model to see if that improves the curve and the fit. We want to make sure the regularization isn't too high or it won't learn any complexity in the model. So you can see that by adding regularization, we're doing a better job of getting a smoother loss curve, and it's also giving us a much less spiky model output. So there are lots of other parameters that you can play around with in the model. You can change the batch size, and if it's too small, it's just going to take a really long time for your model to train. If it's too large, it may have trouble converging. Same with your learning rate. If it's too high, it may jump around a lot and have trouble converging. You can play around with your regularization rate as well. So this would actually be a pretty good model if the training data were less noisy. We have the noise cranked up to 80 here. So if we roll that down to 30 or something and start training this model, this will actually give us pretty good loss. But with the high level of noise, at some point, adding a little bit of feature engineering is going to give us a much bigger improvement than more layers or tuning the parameters. So you can see by reducing the noise, we can get a much better test loss, even only using the linear features. But if we have that noisy data, we're going to need to do some feature engineering to get a better test loss. So we have the noise back up at 80%. Let's add some more complex features. Let's try adding sine and maybe x1 squared and x2 squared. Let's see how our model performs. So one of the major things you notice by adding more complex features is that, especially in the first layer of the model, the features are much more complex. The things that the neurons are learning are much more complex than just lines at different slopes. So you can see that by adding the more complex features, we are learning these curves at a much faster rate. But you can still see that this is a very complex curve. And that goes back to our first pitfall, which is too many nodes in the network. So let's try to get rid of some of these layers and some of these neurons. So you can see that by reducing the number of layers and the number of neurons in each layer, and I also turned down the learning rate, this is giving us a much smoother loss curve and is fitting the data much better, even though we still have pretty noisy data. So the features that we added have helped a lot. And by reducing the model complexity, the number of layers in the model, we are doing a much better job of not overfitting the data. So you can see that even with a very, very simple model of only one hidden layer and 5 neurons, by changing a couple of the other parameters, like learning rate and regularization rate and my activation function, I'm getting a much better test loss, a much smoother fitting curve than some of the more complex models, and it's converging much more quickly.
All right. So this is actually comes to the end of the presentation, but before I end up this presentation, let me share another very interesting demo that you can also play around with it. It's called Teachable Machine. To let me know if you can see the screen. So the concept of this website is actually that you can upload a bit of your own images of your own data, and it can help you train a model on the go. And you can quite straightforward to see the results already. I'm not sure if you can see the screen in the stream. Yes. So probably this link will also be shared to you. It's called Teachable Machine, but I can just give you a very quick demo. So you can have a pose project, audio project, but let's see with a image project. So basically there are two classes. Let's see, this is 1, this is 2, and I will be training a very simple model that I try to use 1 or 2 as input data for that. So I can use webcam, I can see myself. So this is class 1. I will try to have a lot of training data. So I will hold this. So I can just show you that this is 1. And here, this is 2, so it will be 2. I will hold to record, and I will try to create more gestures of 2. Remember, you need to do all these gestures because that's the part of the data augmentation that you need to let the algorithm know a lot of things, that this is 1, this is 2, with different angles of the picture. And now we can actually just train the model. So it will take a bit of time to train the model. It's actually quite fast, and it's amazing that you can already try to check your model. So this is probably 1, right? So you can see the real-time output of it. So this is probably 1, and this is probably 2. So you see the accuracy of 1. Okay, now is pretty stable, but if I change it, it's actually not that stable. Probably the quality of my 1 input data is not so good. But if this is 2, it's quite stable. But of course, you can also try a different gesture. Let's try, what if it's a fist? It thinks that it's probably 1. What if it's a palm? It thinks it's 2. The only reason is because you only give the algorithm the training data of 1 and 2, but not the others. That's why it can only guess this is a 1, and this is probably with more fingers it is a 2. But if you want to try to 1, 2, 3, 4, 5, and all these different gestures, you need to input all that training data, because a model is as best as it can be just with what label data you can have. And you can play around with it. It's not only gesture, right? I mean, if you go to the Teachable Machine website, this website, you can actually play around with it with very different, like this is a hat, this is a keyboard or something else, and you can play around with it and give you a really good sense of what it means as label data, training data, and what it means when you deploy a model somewhere and you can see the prediction results immediately or lively. Yeah, I think that's actually the end of my presentation. I think I can take a bit of questions now.
Thank you for joining us. It was a great session. I'm sure the audience learned a lot. Also, let me remind you again, we are sharing the form for the certificate right now. Do not forget that you have 13 minutes to fill out of the form. If you want, let me move on the question section. Could you send your question to the chat?
All right, I'm also here joining Iknur here. It was an absolutely beautiful session. Thanks so much. It was very detailed, actually. I love about it. And neural networks, actually, we all know that one of the biggest parts of the whole the machine learning and AI world. So thanks so much for a very deep explanation. And before actually moving to the questions, I would like to mention, guys, we're going to be having a secret link, the giveaway actually, link in the chat at a random time in the third session. We're going to be just something in the chat. So just stay tuned and just make sure to join that giveaway also. Coming to the forms link about a certificate, we know we had some inconvenience in the first session. So we're going to be also sending and opening the sessions, the attendance form link in the chat at the same time alongside the Guan's attendance form. So both of the links are going to be on for the upcoming 30 minutes. So yeah, make sure to join them. So I'd like to actually move to the questions. But before actually moving the questions of the audience, I have actually my personal question to you, Guan. Like about the training that you have just showed us about the teachable machines. We have seen that, yes, the data input was also low, but alongside the training also lasts only a few seconds. Do you think is that the also reason for such like the not as stable the result?
So as you can see, when I try to input the training data, it's actually when I hold that button, it kind of constantly capture what's happening in the camera. So you see that I try to put the different gestures of it. But right. Probably some of the gestures, when I move it, you can see you have some like shadows or something like that. Right. So that will create a lot of noise in that. But if you like one, take a picture, probably it will have better quality. There's a recent talk from Andrew Wu, and he is saying that actually compared to just improving the neural network structure, improving the algorithm, it's actually even more important to increase the quality of your data. And I think that's actually, I resonate with it quite a lot. If you have very clear training data, you won't actually be confused the algorithm. You can probably get better results in a very more efficient way compared to just improving the algorithm itself.
Right, like as Luca mentioned in his session, that the trash in or garbage in, garbage out is probably explains that a lot. All right, great. So let's move to audience questions, starting with how to decide which activation function to use between the ReLU and ILU, if that's the difference.
Yeah. So as I said, there are actually a lot of different activation functions, right? So ReLU is one, ILU is one. There is, I think, a recent activation function called leaky ReLU, which, so if you think of ReLU, it's 0 and then it's a linear function. But leaky ReLU means it's not 0. You actually have a bit of a small negative number, and it's proved to be sometimes be more efficient and effective. But as I said, I mean, it's still not a theoretical problem, but rather an experimentation problem. So probably you can, I mean, it's doesn't cost too much for you to try both. You just try it, you run experiments, see whichever works better. And there might not always be a rigorous reason behind it. It's just experiment results. But but still, I mean, the rule of thumb is ReLU, and all this derivation from ReLU, like leaky ReLU or even ILU. Don't use sigmoid anymore. It's proved not to be so efficient anymore compared to ReLU and its derivatives. I mean, the derivation from ReLU.
It's always, of course, better to apply yourself and just, as for example, in the keynote, the Professor Hassan also mentioned that better just do it like in applied work instead of just keeping it in theory, because that's going to just show you a lot. All right.
Exactly. Yes.
So we have one more question by Richard that, do you think is there anything that can replace instead of neural networks, like something that can replace neural networks?
Okay. I'm not sure if I get the question right, but if you're saying something can be as powerful as neural networks to tackle certain problems, I don't see it yet. Instead, it's quite the other way around, that something people think might not actually work with neural networks. Now we can actually tackle it with neural networks. Traditionally, people think that, for example, neural networks are only used for like computer vision, natural language processing, all these cognitive things. But now we find that even something like graphs can be tackled with neural networks, like graph neural networks. Something even the tabular data, we can tackle with neural network quite well. So it's quite still the other way around, that neural network is trying to invade into different areas.
All right. It just added one more. Okay, Yusuf has a question that adding more layers doesn't always mean to have the best result. Like in the TensorFlow playground you have showed us.
Of course, yes. I mean, it's still experimental result. I mean, adding more layers means that you will have more complicated neural network structures, and also depends on how you add it. Certain structures might give you better results, but if it is a very simple tasks, you don't really need that complicated neural network structure, then adding more layers just blindly might just give you even worse results.
Yeah, we have also witnessed that the duration of each epoch also increases dramatically when you add more layers.
Yes. I mean, if you think about the advanced models, right, they have hundreds of thousands of layers. Or if you think of BERT or even GPT-3, they're trained like for months on a supercomputer. So yeah, with more and more layers, it's more and more complicated to be trained.
All right. So one more question by Sharma, I guess. Does our model also depends on the quality of datasets?
Absolutely. I think we just showed that, right?
Yeah.
With all this thing, it won't really give you the good classification of your gesture, but with a very good quality one too, instead of something like this one, it definitely will give you better results. But again, when we use neural networks and when we have real world problems, you won't really always have the perfect data set. You always have noise. And again, you also always have bias in the real data. Like I just mentioned from the GPT-3, they even have make some discriminative words among certain groups of people. So those things we need to be careful, and we at least need to be aware of. And we need to at least be aware of that and find ways to actually imitate them whenever possible. So that's
we are always
that's
going to have
another-
errors, but trying to get the lowest is better.
Yes, yes.
And one more question by Nilla is there any state-of-art open source library to detect objects which can be used to build our own model?
TensorFlow. There's a module from TensorFlow called Model Zoo. So just go to the TensorFlow repo. You will find the Model Zoo. Within the Model Zoo, you will find all kind of models, from computer vision to natural language processing. Object detection is one of them. You can even have fancier tasks to tackle with. But just go to Model Zoo in TensorFlow. You will find it's all open source. You can some models will be very large, like several gigabytes, but there are also simplified models. Some are specifically designed for mobile phones, so it's much smaller that you can just try first to give you a first sense of how the model works.
All right. Again, well, thanks so much for taking your precious time. It really means a lot, and this session actually was absolutely great. So thank you again for joining us, for attending. So if you also have any questions about, yeah, of course, it's a great pleasure. All right then. Thanks so much again. See you soon.
Thank you. See you.
All right, guys. We're going to be moving our last session with Brett, and we're going to be covering artificial intelligence in a bit. So meanwhile, let's give a quick the break right here, and let's move our last session with Brett. All right, Brett, welcome. How are you?
Welcome. Good day.
How are you doing?
Good. Greetings from a little bit away from the other side of the world, we'll say.
All right. Hope your day is going so well so far. So we are actually in the last session about artificial intelligence. So I would like to actually ask you kindly to introduce yourself, what you do, what's your background, and what kind of topics in general, what you're going to be covering today.
Sure. My name is Brett Kuntz. I'm from Missouri in the United States. I've done a lot of work with mobile phones, so apps, that sort of stuff over the years. And in the past few years, I've been working a lot with, I've been really interested in this idea of getting stuff and running it on your phone. Although recently that's kind of expanded to be like more than just phones, we'll say, like little bitty embedded devices, stuff like that. So I think this is kind of just a interesting area in the field that's up and coming right now, and that's what I've been interested in. Yeah.
All right. What about the content? Like, what kind of like specific? Do you have any specific titles to cover up today, or?
Sure. So today we're just going to talk about sort of artificial intelligence in general. This is it's a large and broad field. So I thought I would just try to give you all sort of how I think about how it all fits together. And then hopefully that will sort of give you sort of a reference point for.
Yeah, I also do. Because as you know, like the AI is almost like heard everywhere right now, but nobody really knows how to start or how to continue and so on. I'm really hoping that this session is going to be very helpful for us, also including me. So if you don't have any questions to me or regarding anything, just feel free to start. The stage is yours.
Okay. Yeah, right. I put at the very end, I'll sort of talk about how you all can get started.
All right. I'm in the backstage then. See you soon.
Share. There we go. Okay. Good morning, and sorry, good afternoon for you all, and thank you all for stopping in to listen, and thank you, Vishal, for inviting me. Today we're just going to talk about artificial intelligence. This is sort of like a very large and broad field. So like I said, I thought I would just kind of give you like sort of my take on things, how I think about how it all fits together. So towards that end, we'll sort of look at sort of the history. We'll say where we came from. We'll look at neural networks and some of their some of the different types and interesting historical milestones in building this field. Along this way, then we'll sort of talk about some of the interesting applications, sort of problems that have proven themselves to be approachable by these techniques. And then at the end, we'll sort of talk about the scaling hypothesis, just this idea that in the upcoming decade, we're just going to be building things even larger and with more and more data and compute, and what the potential implications of that are. And then from there, broadly, we'll try to sort of look forward towards the future and try to make some predictions about the future of this field. So here we go. Really, we have to go all the way back, we'll say. This gentleman on the left here, this is an early picture of Alan Turing, who was an important British mathematician during World War II. He did a lot of theoretical work, but one of the things he developed was what were called Turing machines, sort of this idea that by encapsulating state and sort of following a certain set of patterns, you could sort of build machines, or more broadly computational machinery, in order to sort of tackle larger and larger problems. Sort of the theoretical framework for computers as we know them today. The gentleman on the right is a gentleman named William Shockley. He is one of the key people who invented the transistor, literally just a tiny diode that you could turn on and off. But the combination of these two things, sort of, we'll say, the theory of the computation and then the practice of actual circuits, transistors, combined together to produce integrated circuits and then more broadly computers. But really, a lot of it really comes from these two gentlemen in the 1950s. What's interesting is that a surprising amount of this field was really, these people back then were actually thinking about it and inventing it and working on it as early as like the 50s and early 60s. Symbolic logic, this idea that we can sort of solve problems just using nothing but pure reason. If we can sort of create truth systems and things like that, was a well-established field very early on. The statistics people were not to be left out. They understand very early that they could use these devices to sort of approach problems using statistical methodologies. And so really, I would say that machine learning proper comes out of this era, we'll say. This combination of sort of computers and data and then a little bit of statistics was really, I think, actually established way back then. This gentleman over here on the right, is a gentleman by the name of Frank Rosenblatt. He was a psychologist, and in 1959 he invented something called the perceptron. This was a way sort of taking an input, and then you could have a computer sort of learn the differences in the inputs and stuff, and then have it output a result, an output neuron. Kind of really the birth of this whole neural network field. So, 1959. So now we'll kind of fast forward to not quite the present, but we'll say 2010 or so. But honestly, like I said, I feel like a lot of this stuff was already there at that point in time over 50 years ago. Basically, computers got faster. We gathered more and more data. But we found really that a lot of these sort of basic algorithms that were used in the early days actually sort of did a reasonably good job of scaling up. One of the joys of statistical approaches is basically as you add more and more data, they get larger and larger, but they still, generally speaking, continue to work, and you can tweak them easily. And you can add more and more of these sort of small models. And so basically the whole field of machine learning, I would say, sort of dominated the field up until around 2010 or so. So I put this graph here because I think it kind of illustrates the key idea. But basically deep learning, really, the pieces were there, but what we needed was basically more and more data and more computational power before these sort of approaches actually started to make sense. So we can argue about sort of this point where the green line crossed the red line, but we'll say probably the key moment was sometimes whenever somebody started doing this stuff on GPUs, so somewhere around 2012 or so, we'll say. But yeah, for most problems, long before you start to try something with deep learning or anything fancy like that, you should actually sort of look into the tool bag of tricks that machine learning has picked up over the years and start there. You know, if you have something working with machine learning, deep learning may make it fancier, better. But if you can't get it working with machine learning, then deep learning probably isn't going to help either. So what we'll try to do now is sort of go through a whole bunch of different types of neural networks. I think one of the best places to get started with neural networks is just this field of what's called convolutional neural networks. I've talked about this a decent amount over the years. Up here on our upper left, we have our little bitty perceptron, just literally mapping an input to an output, like I said, from 1959. The basic problem with perceptrons is that they sort of try to do too much, to try and go from sort of the beginning to the answer. It's asking too much of the neural network. And so the next big step was what we invented was called feed-forward neural networks. But they just sort of add this set of green nodes, this set of what's called a hidden layer. And this sort of allows the layer of indirection between the input and the output, but this actually makes it much easier for the neural network to sort of learn the patterns and representations in the data. If one layer of indirection is good, then two layers is even better, so to speak. So we have sort of deep feed-forward networks, sort of an input, two layers of hidden or indirect nodes in our output. This is a really common pattern, and you'll see it in a whole bunch of different other places in this field. So I think it's a valuable one to pick up. Convolutions are sort of just another area of sort of computer vision theory, although they've sort of expanded out to tackle a whole bunch of other things. I think the key idea of convolutions is just basically that they're a cheap way to sort of break up data and work with them. And so by extension, they sort of, by combining them with neural networks, we sort of have convolutions to sort of do some of the heavy lifting, and then we sort of use neural networks at the end to do the actual sort of pattern recognition steps, so to speak. So this bottom thing is simply just trying to illustrate a deep convolutional neural network. We have an input, a set of convolutional layers, two hidden layers, and then finally our output layer. This may seem like sort of a theoretical approach, but what we're looking at right here is actually the state of the art for image recognition in this field as of about 2014. This is called the VGG network, and it's quite literally nothing more than convolutions. We'll say an input image, set of convolutions. Sort of this red is a max pool, which is sort of a step to squash the data down. 2 more sets of convolutions, max pool. 3 sets of convolutions, max pool. 3 sets of convolutions, max pool. And then finally, over here, these blue nodes is literally 4,096 hidden layer, a second layer of 4,096 nodes. And then finally, we have 1,000 output nodes to sort of map to our results that we're looking for. ImageNet is a slightly larger data set. It's like 1 million images or so, but it's a really good practical way to sort of test these sort of convolutional neural networks at scale. ResNet is a paper that came out about a year later. This is a really important milestone for this field. The basic idea of ResNet, the basic problem with this convolutional approach, we'll say, is that as we sort of go from the input to our output, the more and more layers we put in the middle, basically it becomes harder and harder for the network to sort of learn. And by extension, any sort of noise or whatever in the process quickly creates limitations to that approach. So ResNets really are a very simple thing, but basically we just add this sort of skip connection, this sort of extra layer to our network that's skipping around our nodes. And this is literally done at the programmatic level of just simply adding our input back to the output of our network. And but this simple little trick really allows you to build larger and larger networks, say thousands of layers. It's been proven to do, and you'll see increasingly in some of our later slides. And so it's a really valuable paper for you to know. Convolutions sort of, we can say go from an input image to a result. This works great for, say, visual data, but many other problems in the real world actually sort of need to be reasoned about using sort of a time sort of approach. So recurrent neural networks are the really important other area of research that you need to be aware of. This is an older paper from 1986 or so. Whenever people sort of draw a slide, they usually use this rolled form over here on our left. So we sort of say, have a set of nodes, and then we have this sort of loopback node. But I don't really like this way of visualizing it because it kind of like makes it a little too mind-bendy for me. So this sort of unrolled form, I think, is a better way to think about it. We sort of have an input, phase 1, phase 2, phase 3, phase 4, where input. We sort of map the initial input to a node and then to the output. And then the second one sort of takes some of that input for its output. The third one takes some of the second one in, and then so on and so forth. And then this is a really powerful approach because, like I said, we can start to model time series data and, crucially, language, as we'll see. The basic problem with this sort of recurrent approach is that it's a little bit too simple, we'll say, or rather, it can capture sort of recursive forms and stuff like that, but it has a real tendency to get stuck on sort of repeating itself. So the next important paper in this field is what's called long short-term memory, or LSTM modules. This is from a gentleman named Schmidhuber in 1997. On the left, we're sort of seeing our RNN architecture, sort of how the actual math works underneath the hood. So the LSTM sort of adds this sort of state and this internal history sort of tracking thing. And then the module itself can sort of remember things or sort of choose to forget things, assuming that another node down the line will remember the thing. And so this actually dramatically improves this sort of basic recurrent approach and really allows you to start to model long-range dependencies and stuff, which is to say things like text and stuff, but also LSTMs have been used in other domains such as video and things like that. So the seek-to-seek This is a paper from 2014 that sort of used LSTM modules to translate language. So the key idea of the seek-to-seek is this sort of what we're looking at right here. We sort of augment our input data in order to significantly improve the results of our output network. So we take this sort of ABC, we'll say, in one language, and pair it with sort of the WXYZ in another language as sort of a tied inputs. And in these two things, we map them together, and then we reward the network for sort of learning the output, the original output. So conceptually, we might take a sentence in one language, like I am a student, and then we compare it with its pair in another language. So like the Spanish form, yo soy estudiante. But then combining these two together, we tell the network to learn that whenever it sees I am a student, it's supposed to output yo soy estudiante. What's interesting then is that whenever we start to expose this with lots of data and many, many samples, you can give it like a new example, like I am a teacher, and the network can begin to correctly predict what that result would look like, even though it hasn't really seen it before. The key idea of this is sort of that the network's starting to learn sort of long-range dependencies out of the data it's seeing, which brings us sort of to this transformer model, which has become really popular in the last couple of years. This paper came out in 2017, and conceptually, you might think of it as a larger, much more complicated sort of version of our LSTM module from before. But basically, this approach has really taken the world by storm, so to speak. It's proven itself in a whole bunch of different domains, as we'll see here in a second. So what we're seeing here on the left is just trying to illustrate sort of how the transformer architecture looks, how it's modeled, so to speak. These are sort of the bits and pieces. The key concept right there that you might stare at is this NX right here. Basically, one of the key ideas of the transformers is while we're doing this, we can also do this in parallel. So we can have a whole larger collection of these sort of things running at once. And so over here on the right, this is just sort of, we're getting a little bit ahead of ourselves, but I'm just trying to show you that transformers sort of perform better than LSTMs on larger and larger data sets, and even for the same amount of compute and things, they're actually, generally speaking, outperform these LSTM modules. So that's part of why they're a really important step forward for this field. And so this is a paper that came out pretty recently, actually, from Facebook. I don't know that you necessarily need to know it per se, but I threw it up here because I think it's really important to understand that a lot of modern networks sort of use these sort of different pieces together. So at the top, we have sort of like a cat picture, we'll say. We're running it through a convolutional neural network and sort of taking its outputs. At the bottom, we sort of take a sentence describing this picture. So a cat with white paws jumps over a fence in front of a yellow tree. We run it through Roberta, which is sort of like it's a variant of a transformer network, we'll say. We take the outputs from that network. Then we concatenate, literally just sort of squash these results together. And then we run a transformer on top of that. But what's really interesting is that we sort of get what a full-blown sort of logical model right here. Literally, the network can sort of say, oh, you know, the cat part of the sentence refers to this, you know, this cat that's jumping. The yellow tree is sort of this piece. White paws, it can literally sort of pick out the individual paws of the cat. And then it can sort of also know what else is not in the picture, so to speak. And so this kind of really gives us really powerful sort of way of sort of combining convolutional approaches with natural language approaches to sort of produce like a object detection network that can really start to sort of almost sort of reason about a picture, we might say. And so then if we can think about sort of building a larger network by combining pieces of networks, then we might also start to make the next logical jump and think about having multiple networks working together to solve a problem. So GANs, or Generative Adversarial Networks, as they're called, are an idea from 2014 or so. The basic key idea is you have sort of two networks sort of battling each other in order to work together to produce a common result. What we're seeing here is what's called StyleGAN. This is a paper from 2018 or so, where the computer is literally sort of hallucinating these faces. This is just all sort of what the computer thinks that we would think a face would look like. But as you can see, these results have started to become sort of really realistic looking and stuff like that. And so a lot of people are really, really interested in this area right now. A full breakdown of how GANs work is maybe a bit beyond us right here. But the sort of the key idea is that we have sort of two networks working together. So the first network is sort of training itself to recognize pictures. And then the second network sort of training itself to fool the network that's recognizing pictures. So this is what we're looking at here, sort of the loss training curve for a GAN network as it works. The key idea then is this little spot down here where I've put a blue star, where these sort of loss curves cross over each other. What happens is that the first network sort of learns, and eventually it sort of starts to become stable. It starts generating consistent results. And at that point, all of a sudden, the second network can sort of leapfrog it and sort of start to learn on top. But then what's interesting is as the second network starts to improve, the first network actually starts to have to improve as well. And so together, these two networks working together can kind of reach a much better understanding of the problem than either would it be able to do so on their own. So this is kind of a really interesting concept, and one we'll see again and again as we go forward from here. Reinforcement learning is a whole large field in and of its own, kind of separate from neural networks, but much like we saw with machine learning sort of being overtaken by sort of these deep learning methods, as of a few years ago, sort of these neural network approaches have become really, really commonplace in this field and are increasingly sort of being where the new stuff is happening. So this is from a paper from 2015, illustrating what's called a DQN, a deep Q network. This basically takes an input image, or set of images more properly, but basically the screen capture of an Atari video game, runs it through some convolutions, a set of fully connected layers like before, and then finally maps the result to actions. So what it thinks that the joystick should do, so to speak. But what's interesting is that this fairly basic looking network, if you look at it, can do state-of-the-art, or rather can play Atari better than a human after a little bit of experiment on a number of different historical games. So this has kind of been an interesting area where the DeepMind team in particular has really been trying to work to sort of be able to tackle these sort of video games on the fly, sort of create these agents. They can sort of say, we'll say see something, and then reason about what the best thing to do next is. Which brings us then to sort of the AlphaGo family of engines. I've done a couple talks on this, so if you're interested in this particular subject, you might go look those up. But the basic core concept of there's the AlphaGo engine itself proper. There's a few different variants, but the AlphaZero one in particular, I think is really interesting as sort of a milestone for reinforcement learning. If we look over here on the left, what we're seeing is how the actual AlphaZero network was put together. But what's interesting to me is it's literally 40 of these residual layers, basically the same concept from the ResNet that we were looking at before. combined with sets of 3x3 convolutions and batch norm. Sort of, we'll say the same building blocks as our VGG network plus our ResNet, and then sort of a custom output logic up here at the very top. But other than that, it's just really a very, very large network. Conceptually, there's not really a ton of magic here, so to speak. Or rather, the magic's in its size, but not so much the methodology. So over here on the right, what we have is sort of the training curves for the AlphaZero as it was sort of learning to play by playing itself over time. So this purple line is sort of maybe our traditional machine learning style approach. This is sort of the original AlphaGo master engine, we'll say, but it's trying to learn from human games. So it actually does really well, as you can see, actually at the start. It very quickly improves, learns from the games that's shown, sort of improves rapidly, and is able to play the game at a high level. But ultimately, we might say by having human input almost, or by by learning from human games, in turn, ultimately it's limited by human games. So then what's really cool to me is sort of this dark blue line, which is sort of illustrating how the AlphaZero engine is training over time. As you can see, the AlphaZero actually starts out really poorly, we'll say. It plays the game terrible for a long time compared to the other engine. But somewhere over 20 hours to get in, it started to teach itself how to play the game. And it's sort of improved to something on a similar level with our AlphaGo Master engine. But then after that, it's sort of just doing its own thing, we'll say, so to speak. And it's able to steadily improve until it's like beyond any human player has ever been. And by extension, it's the greatest Go bot of all time. And I think this is just a really, really interesting milestone for reinforcement learning and AI in general. So this is from the AlphaStar paper, which came out in 2019, where they were sort of taking the same concept of trying to do a reinforcement learning, but apply it to the domain of StarCraft. So a slightly different and a significantly more modern video game. What we're seeing here on the left is just sort of how the actual neural network for this thing works, sort of how it's all put together. It looks really scary, but I don't think it necessarily has to be so. But we might think of this as being a really complicated set of inputs. We're sort of trying to take a bunch of different pieces of the StarCraft game and sort of map them together. The core, though, if you look, is just an LSTM module, the exact same stuff we were looking at before. And then all this stuff on top is sort of, we'll say, kind of a fancy output, just to sort of give the model the ability to sort of control units and stuff within the video game. So at the top then, this upper right corner, what we're seeing then is just sort of the progression of the different reinforcement learning agents as they played over time. Quite literally, the agents would sort of learn a strategy, and then once they learned a strategy, they would quickly start doing it all the time. And then after a while, the other agents would have to learn a counter strategy, and then sort of these sort of strategies versus counter strategies and so on and so forth. We can see over time that the group as a whole is steadily improving until at the end, it was able to play against human players and be competitive. What's wild to me is we might think of Agent 600 over here. This agent down here in the bottom right is sort of making moves in response to attacks that the very first generation sort of came up with, even though it's never even seen this original player, but it's actually sort of, knows how to battle them, so to speak, without actually having ever really encountered them in actual combat or whatever, so to speak. So this is AlphaFold 2. This is another paper from DeepMind last year. They've sort of taken this sort of, this is conjecture, it's not entirely 100% clear how they did this, but they were able to significantly advance the state of protein modeling, sort of using these neural network approaches. The core of this network is probably a transformer model as well, just using some form of axial attention based around the protein MSAs. And so I think this is just kind of a really interesting, these methodologies are not just for games, but we're increasingly seeing them sort of applied to real world problems. And so I think it's really interesting as we sort of see these sort of techniques sort of migrate out into the broader world. I think it'd be interesting to see how many other fields are potentially, we can get massive improvements in our understanding of them by applying these neural sort of techniques. And so with that, I thought maybe we could sort of switch to sort of start talking about building sort of things larger and larger. This GPT-3 model came out of OpenAI last year. And basically, they took the approach from their GPT-2, which was a transformer-based model. This one that's fourth from the right down here at the bottom. And they basically made it significantly larger. So this is kind of a linear model here, but I think it's really just illustrating how much larger the GPT-3 model was than these various predecessors, so to speak. An extension Y was able to significantly capture much more data about the data was shown and be able to build a larger and much more complicated and powerful model by extension. So there's this essay on the internet called The Bitter Lesson by a gentleman named Sutton. But basically, he says that the field of machine learning, as we're seeing up here, for the last few decades, has seen really smart people try to come up with more and more clever ways of sort of tackling different problems, trying to add more and more domain expertise. But at the end of the day, sort of the approaches that have won out, the approaches that have sort of proven themselves, hasn't necessarily been complicated approaches, but rather simpler approaches. And so I like this little guy down here at the bottom who's just sort of saying stack more layers, because it kind of just sort of illustrates this sort of mentality that, let's not be smart, so to speak, but rather let's just see if we can make things larger and larger, and we'll see what the heck happens as a result. The thing is, if we can get better and better results by building things larger, then I think the question is simply, why aren't we trying to build things larger? Why try to be smarter than the machines if this is how the best way for them to sort of learn problems is, really, at the end of the day? So this is an interesting paper from a gentleman named Kaplan, which is sort of illustrating that across basically all these sort of different domains, we'll say, that basically as we get more compute power, which is to say bigger and bigger computers, as we get more data, just more and more data, we can build larger and larger models. And so by extension, if we can build if we have a larger computer and we have more data and we can build a larger model, what we can see is kind of this sort of linear sort of scaling, but basically, we can sort of just get bigger and bigger, get better and better results as we continue to scale these things up. Look at the slide on the left, because here's basically a later version of the same thing. The key concept then down here at the bottom is that this is up to 10 to the 4th. So what we're seeing is sort of, even with 3 orders of magnitude more compute power, that we're sort of seeing these trends still hold, and by extension are able to continue to sort of improve the loss on this language model even further. So here's a slide from OpenAI. a little while ago, but I think it really illustrates sort of everything I've been talking about here today all together. If we go over here on the very bottom left, we have our invention of the perceptron way back in 1959. As we see over time, basically computers continued to get faster and faster. And as a result, we were sort of able to build larger and larger and more powerful approaches. And then somewhere over here, like I said, 2012 is probably a reasonably good spot to sort of prediction in this era. What we can see is the sort of compute has grown drastically. We've been able to build these approaches, more and more powerful approaches, and you sort of utilize these sort of approaches in a much more interesting ways. So we have here the AlexNet, sort of the paper that put deep learning on the map with the ImageNet competition that year. There's the VGG model we were talking about before, our ResNet shortly thereafter. The neural machine translation is sort of relative or semi-related to the seek-to-seek paper I showed you before. The DOTA one here is sort of similar to the AlphaStar paper, we'll say. Up here on the top, we sort of have the AlphaGo 0, so you can kind of conceptualize how much compute power it required. And then if we added the AlphaFold paper to this, it would be a little red dot somewhere around the Z, the O, and the 0 up there, and the AlphaGo 0, if that makes sense. Oh, and then our DQN is down here below, somewhere around 2015 or so. So to me, the first clear trend that we can see out of all this is simply that compute power is only going to continue to need to be scaled up in order to sort of build these devices. Google's been kind of at the forefront of this with their TPU machines. What we're looking at here is sort of the TPU V3 cluster, which has a large collection of sort of customized edge AI processors, literally compute devices designed specifically sort of running these sort of neural network or matrix multiplication math, and then sort of all working together as a whole. I think this is just a kind of really interesting area in general because these same sort of devices that we can use up in the cloud, so to speak, can also be sort of individually split out and then run on device in the field. And so this kind of gets this really interesting sort of feedback loop where we can sort of do things in the cloud, but we can also sort of then very easily distribute that same logic to devices in the field and sort of run them where they're actually needed. A key piece of how all this works isn't so much the compute processor itself, but sort of the RAM, we'll say, sort of the amount of memory and state that the processors can hold in memory and sort of work with. And then sort of the key flip side of this is sort of bandwidth, sort of the ability for all these nodes to sort of talk together. So one of the key capabilities of how the TPUs work is they have sort of a dedicated network for all these processors to talk together, and by extension, be able to work together on larger and larger problems. Sort of the field of high-performance computing, sort of supercomputing, we'll say, in academia and the government, has maybe we'll say sort of resisted sort of these neural network approaches the last couple of years. But I think in the last year or two, they've really started to get on board with sort of building, sort of rethinking how we're building supercomputers in order to sort of make these sort of computationally things sort of run better and larger at scale. I mean, key concept of this is sort of what we'll say systolic designs, but just very broadly, making sure that the compute and the network and the RAM are all sort of working together in harmony. And so one or another isn't trying to starve each other. More and more data. I think it's only clear to me that data sets are only going to get larger, and we're going to have more and more of them. These image recognition models I've shown you are actually, if you look at their actual inputs, usually only using, like I say, a 200 by 200 or slightly larger samples to sort of try and reason about the world. So to me, like whenever you start talking about, say, 4K video running on device at 60 frames a second, I think there's still a long, long way to go with sort of being able to run these things out in the real world on device in real time, and sort of building things that can run that away fast as possible. Our ability to gather data has only gotten better over the years, and so we're able to build larger and larger data sets. And by extension, these data sets are starting to scale up to gigabytes, or even as I'm showing you right here, terabytes in size. And then, there are various internal data sets at some of these large companies, which are petabytes, and people have even rumored of larger ones out there. The key piece of all this is just sort of annotating your data in general. A lot of work has, I still think this is sort of an open problem, just finding better ways to sort of annotate data. And then sort of the second lever of this is kind of a field that I think is poised to become really popular in the next year or two, but just sort of this field of semi-supervised learning. Sort of, we label a little bit of data, we sort of use the computer to use our few labels to sort of try to make sense of a larger set. And then by sort of iterating between these two, we can sort of build up larger and larger data sets without actually having to manually look at every single picture, which doesn't scale, so to speak. And then, this right picture is from a large data set called the Pile. It's a group of volunteers put together this data set. It's nearly a terabyte in size, and it's their hope or belief that they'll be able to train a GPT-3 style model using just this. And then the other really interesting thing to me is just sort of R&D in general, we'll say, sort of just our theoretical approaches to all this. The basis of all the neural network methods I've shown you today is a sort of set of algorithms around what's called automatic differentiation, or more broadly, the backpropagation algorithm, which is to say that everything I've shown you today is kind of like a very, very fancy forms of matrix math, just done at larger and larger scales. But what's interesting to me is that as we sort of try to make these matrix multiplications larger and larger, we sort of start to hit some fundamental limitations with how fast all the nodes can communicate together and stuff like that. And so it's not, that's where to me a lot of the interesting research is going on right now. This slide on the right is from a paper about predictive coding that came out last fall, where they're sort of trying to make the neural network sort of learn sort of how to do its automatic differentiation itself on sort of a node by node basis. So you don't actually have to have sort of a global update step, which is just kind of really interesting, because something like this could potentially significantly reduce the amount of interconnections that's required, and by extension sort of allow us to sort of rethink this sort of backpropagation sort of algorithm approach that sort of seems to be the foundation of things where they are right now. There's a couple of really interesting software projects. They're sort of trying to rethink this whole concept of scaling all this stuff so we can build larger and larger networks. This JAX project is from a team at Google. They're sort of trying to rebuild the foundations of sort of generating code to run on TPUs that's extremely performant and efficient. They've had a number of interesting successes in the MLPerf competition. Notably, last year they trained like a BERT network in about 30 seconds, which was pretty wild. ImageNet network in 30 seconds, which is pretty wild. And then this DeepSpeed team works out of Microsoft. They're sort of working in conjunction with the OpenAI team there. But they've done some really interesting stuff with sort of trying to improve parallelization and sort of try to reason about how to build larger networks without necessarily having to have a supercomputer on demand to run all this stuff. So I think that's just a really interesting project to have on your eyes on as well. AI, like I said, is not a new field. In the 1960s, it sort of came out and became extremely sort of hyped. And so at that point in time, somewhere around 1970 or so, they had the AI winter, what they called. Basically, the claims had gotten more and more outlandish and hyped, we'll say. And then it became clear that the field wasn't going to be able to sort of deliver on all of its promises. And so as a result, a lot of funding disappeared. And by extension, sort of the, things went quiet for a few years, decades, literally. So a number of people look at sort of the, AI is certainly pretty hyped right now. And so a number of people look at it and they sort of say, is this all going to happen again? I can't speak entirely to the future, but I don't think that the situation is quite the same this time around. To me, the big reason that the things fell apart in the 1970s is simply that the commercial applications of things just wasn't really figured out at all. So today we have sort of this whole Bitcoin mania, or just crypto in general. I don't see that going away anytime soon. We have all these commercial applications of these sort of neural networks. So computer vision and natural language processing, like I've shown you, have really thrown a lot of interest in this field because they can solve real-world problems on a day-by-day basis. I've not talked much about recommendation systems, but this is a really, really large area of real-world sort of modern production sort of AI systems and stuff like that. Or rather, if you've ever clicked on an ad somewhere, then you're someplace, there's a recommendation system that's processing your input. And then, like I said before, I think this concept of autonomous devices, I really don't think these ideas are new, but in the last decade or so, we're finally able to sort of build all this sort of compute and power and everything to where we can actually run things on device and sort of start to do things in the field. And I really think this opens up a whole world of interesting sort of just real world applications for things to be tackled using these sort of AI approaches. So to me, all these things above just basically aren't going to go away. And by extension, they're driving revenue at large companies. And so by extension, I think that all of these above are only going to mean that we're going to have more compute thrown at these sort of things, more data, and ultimately more R&D in the future. So as a result, I don't feel like the AI winter is going to happen again, or at least not the way it happened the last time around. Which leads us then to this sort of broad question of whether or not we can actually develop some sort of general AI, or AGI as it's sometimes called. I think the broader question, or the real question, or one of the tricky questions simply is, what is intelligence? We have this ability to reason, to interact with our environment, to sort of solve new problems, but can we define that in a way that, is something that, what is it about us that makes us different than everybody else around us? And by extension, are we sort of special in this universe? There's this sort of school of thought that, if a computer can do it, then it's not really AI, it's just a fancy math problem. And I think there's a certain truth, that we might say that being able to play Go at a high level, sort of that sort of super specialized neural network, isn't the same as sort of, not tripping over your shoelaces whenever you walk down the street. But I would play off sort of what I was trying to go at with the alpha star thing earlier. We really don't, you don't really think about how to convert, say, the air you're breathing into energy, but there's all these sort of processes that are inside of us that have all sort of been figured out already, but you don't really think about all that. And so, really, we may think of ourselves as being generalized, but that generalization is really only on top of a whole large pile of sort of specialized sort of subroutines, sort of that's sort of the process of life, we'll say. And so I think, as we get more and more of these pieces, as we build these systems larger and larger, I think it's entirely possible that we may find out that, simply a certain amount of compute density is simply the key to sort of actually reasoning and stuff like that. I will say that all the problems I've shown you today are sort of, we'll say, closed problems. We sort of have a mathematical and objective function, and then we're sort of solving this sort of math problem to try and sort of minimize loss or not lose on a game or something like that. But we sort of, in the real world, we have sort of this open world problem where we're just trying to sort of interact with the environment and figure it out, and then by extension try to maximize our results. So it's entirely possible that we're thinking about the problem all wrong, and it'll ultimately be something much more complicated than just a pure math problem. Having said that, I found this article on the internet from a group of people who are sort of attempting to make projections about when AGI might be possible at a high level. I'll link this thing at the end. It's just a really interesting sort of article where they sort of explore a lot of, if this is the limits of intelligence, then, when could we potentially be able to build a computer that could do something simpler? At the end of the day, sort of, they're mixing a bunch of Gaussian models together to sort of arrive at this projection. So it's sort of guaranteed to converge at a sort of 50% probability at some point in time. But I think this sort of idea that, we'll say sometime in the next century, we could potentially sort of either know whether or not these approaches are going to scale to sort of solve this problem is just a really, really interesting one, and something that I think is going to be really interesting to explore in the upcoming decade. So to me, this whole next 5 to 10 years, I think is just really interesting because it's really going to show where we are at on this sort of curve and whether or not we're being too optimistic or whether or not, there actually could be something there. So with that, I'd like to say that the future, though, is you. None of the techniques I've shown you, none of the modern era techniques I've shown you were literally possible 10 years ago. And so by extension, I think you can't really say what's going to be possible even 10 years ahead in this field. And so you may think everybody has sort of a gigantic advantage on you and that you can't possibly contribute, but I would say quite the reverse. There's literally never been a better time to get started with these sort of techniques. All this knowledge is really, where it once took years to learn, now you can learn it in months or even weeks or sometimes days. There's whole sets of tutorials and whole groups of people online. And so there's just a whole gigantic community of sort of people out there that are interested in this stuff as well. And so if you're wanting to get started on it, you can very much jump in and get going. The best route to do that, I would say, is to go through the Fast AI courses. Jeremy's done a lot of work to sort of simplify all these things down, sort of really try to make it as simple as possible. You should get yourself a GPU if you can. Just sort of start doing stuff on your own device. Then you don't have to worry about cloud credits or any of that sort of stuff. And then broadly, I would suggest that you try to find a problem, just something that's interesting to you, and then sort of see if you can find a way to sort of tackle these problems, bring these sort of theoretical techniques to a real world problem. And then by extension, you can sort of become the world's sort of domain expert in that tiny little niche. There's a group of people on the internet, this Eleuther.ai site. They have sort of a Discord server you can join. They have a number of interesting discussions, and if you're looking for just sort of a source of new ideas and stuff, I would highly suggest you join their setup. And with that, I'll say thank you all for listening.
All right, great. But that was actually an amazing presentation. Did you just make it all from scratch?
I did one last year, we'll say, that I stole a little bit of the content from, but I updated with some new slides and some stuff I've been thinking about recently. So it's been rattling around in my head, and this gave me an excuse to sort of
All right.
Brett, could you please share the slide if you can, because there is a request from the audience.
Yeah. I have a website, brettkunz.com, and I will, right after this, I'll go post my slides there.
Oh, all right. So the Brett, I'm gonna sharing this site, guys, right now in the chat. That's the website of Brett. So make sure to visit that. It's always making like there's a blog website, so you can also know more about that. There. Here we go. So, guys, any questions if you have in your mind, just feel free to ask in the chat. We're gonna be displaying and just trying to find
some questions, by the way,
all right,
about cryptocurrency.
Probably, but I see people trying to tackle financial problems with AI, and I would probably go backwards to traditional sort of. There's a whole world of people who do stock trading and stuff off of, well understood machine learning and stuff like that, and I would start there before start trying to throw deep neural networks at anything or something like that. Learn the existing theory before trying anything new, I would say.
Well, like whenever I have actually like to ask this question to any AI engineers before, like without even like letting me complete the question, they're like, no, impossible. There's no way you can do it.
There's a company called Jane Street, and they do a lot of really interesting stuff with algorithmic trading, and so you might research them and some of the stuff they do.
Oh, sure. We can just look that in the Discord. I will try to also share in the community afterwards. So I have actually one more question from myself regarding the AI. So as we know, like especially like scrolling down Instagram, you see like the memes there regarding AI and so on. There's always saying that anything that's standing behind the AI is actually the math. So how accurate is that? Like, is it AI really consisting of just math?
Well, yeah. Well, maybe I'll get people angry at me. Definitely, the foundation is math, I would say, but I think perhaps the mathematicians try to take credit for everything, and I think there's a lot to be said for all sort of the computers and whatnot on top. And then also times I think the computer people sort of try to take credit for stuff whenever the statistics, I think that's really kind of like the key thing. It's not so much the pure math, but just sort of understanding probabilities and reasoning around that. One of my personal frustrations, we'll say, is sometimes you'll read a paper and they have like a pile of math this gigantic.
Exactly, yeah.
And you go, oh my gosh, what the heck is that? And then you go look up the actual code, and it's literally, well, thing A plus thing B plus thing C, and then they multiply everything together. And oftentimes the code implementation is way much more clearer. So that's something I often do. If I don't really understand a paper, I say, okay, show me the code. And if they don't have code, that's a real bad sign. But, oftentimes if you can sort of, I think programmers sort of actually have oftentimes the sort of leg up in this field, because, yeah, people love to throw the Greek symbols around, but, multiply something together in a row and then, we have pi functions or something like that most normal people have never seen, but it's just sort of a formalism that's kind of scaring new people away.
Got it. All right. If you have any other questions, actually, from the audience, we will be covering about a certificate afterwards, guys. Don't worry about that. But if you have any specific questions regarding the section on AI, just feel free to ask. But I literally like the history, like starting from the back, like the coming to today's, like it was actually great. Thanks so much for taking part at this event.
Okay. Well, thank you all for having me, and yeah, have a good day.
All right. See you.
Take care. Thank you very much. Okay, we can send the certificate form.
Yeah.
For the last, it's going to be the last one. And
now, whoever.
If you have filled the previous forms, you will be able to get the certificate on Sunday. We will send an email to everyone who filled the forms.
Exactly. Now, as the Hassan also mentioned that the first two links have already been sent in up to as soon as our first and the second sections ended. So this is going to be the last section, and this is going to be also the last certificate. If you were not actually eligible, or if you were not be able to complete the first two forms, even though you actually just complete this one, unfortunately, you're probably not going to be getting the certificate. So you were supposed to complete the first and second forms alongside the third one in order to get the certificate of today's. By the way, the link has been shared in the chat, so you have around 15 or 20 minutes. How much time did you have for the certificate?
Yeah, 30 minutes is enough.
All right, then meanwhile, then you can also introduce the team again, I guess, and kind of discuss the general topics that we're going to be covering tomorrow. If everyone is ready.
Usal, could you please repeat? What did you say?
If everything's done, then we can invite the team again.
Yeah, of course. So while you are filling the form, maybe we can invite our core team members right now. Emre, Yusuf, İknur, Zishan. Yes. Oh, okay. So guys, what do you think? Almost we have come at the end of the first day of Global Summit, Medipol Global Summit. What do you think?
I think it was an amazing experience for us. The speakers were great, and I think people learned so much.
Exactly. I also joined Emre at this point. I also had a lot of questions in my mind. I found all of them in the slides and the explanation. That's why I didn't really need that wasn't need to ask them on the personal at the end. So personally speaking, everything went fluent and so smooth for me.
So
yeah, I agree.
Yeah. Yes, this one.
I really liked Luca's presentation. It was really interactive, and the participants could send the form stuff, and they could interact with the speaker altogether, and it was great.
I'm really hoping tomorrow is also going to be as exciting as today. So make sure also not to miss tomorrow's the session, because we're going to be covering 2 cybersecurity sessions alongside 2 blockchain sessions. So make sure not to miss also tomorrow's event. And I will also like to touch about a certificate of how the tomorrow is going to be happening. So even though today you have just submitted 3 forms and you're only going to be getting 1 certificate at a time, tomorrow we have 2 sections regarding the cybersecurity and as 2 sections regarding the blockchain. If you submit 2 of them, the whole the cybersecurity sessions, you're going to be getting the certificate of cybersecurity alongside the attendance form of the blockchain tomorrow. So you have chance of getting 2 certificates in one day instead of 1. So make sure also not to miss the events of tomorrow. That's probably for me.
And by the way, you can prepare your questions for the Amen Altaher session for blockchain or the cybersecurity one. And maybe because Amen Altaher has 2 sessions, and we will give 5 minutes or 3 minutes in break between the Amen Altaher's sessions. And maybe if you prepare questions from now, you will be able to ask your questions, and it can be a more interactive session. And I want Zishan to mention about the details of tomorrow's sessions, the time and the sequence.
Of course, tomorrow we have at 13 Malak Malkavi. He will be talking about cybersecurity power between past and future. Then at 14, Abdullah Ismailov will tell us about what does a cybersecurity expert do. And at 15, we have Amin Altahir. He will introduce us to blockchain technology. And at 16, again, Amin Altahir will talk about blockchain in the future. And lastly, at 17, we have Tawfiq Sahir talking about software development lifecycle and hackathons.
Yes, as you said about Tofi and Arkis Academy, CEO of Arkis Academy, I want to mention about the Arkis Academy. They have some trainings, some skill tests, and we are going to send a link from Arkis Academy. And if you fulfill the form, the conditions of this form, you'll be able to get, actually 30 people will be able to get a free endurance participants rights And after a while, we will send this link. And don't miss the TOEFL session as well at 5 p.m. Right? They have they will mention about the endurance, which I have mentioned about the this hackathon at the beginning of the session. And don't miss that. It is really important. And software development life cycle and the hackathons ecosystem. So what else? The giveaways. Yes, the giveaways. Yusuf, could you please mention one more time giveaways? Don't forget to follow us on Instagram page and join our giveaways. But what kind of giveaways? One more time, please mention.
Okay, Berkay. As we mentioned again and again, we have lots of giveaways on DSG Medipol Instagram account, and everyone can join them until Sunday. And we will announce the winners live. And that's all about giveaways.
All right, one more thing from the chat that I just noticed by Yunus Emre. It's just asking if I missed anything. No, Yunus, you didn't actually miss anything. The matter of fact that about the certificates, they're not going to be sent at the end of the day, but instead all of them are going to be sent at the end of the summit. So please just try to attend all of them. So all of the certificates that you're going to be earning, you're going to be getting through your email in one day, which is going to be the day when the summit ends. So at the end of the days, unfortunately today or tomorrow, they're not going to be sending any certificates because they're going to be process of elimination. And after that, we're going to be probably sending the emails, which is going to be Sunday night or the Monday next week. So the link has been also shared, by the way, in the chat. That's going to redirect you to the WhatsApp groups or direct you to the giveaway page, which is our Instagram page. So make sure to attend. There's always a chance to win something, so do not hesitate to join.
Thank you very much. By the way, as Merve mentioned at the beginning, and there are lots of Google communities under the Google developers, and we are live on the Google Communities Turkey YouTube channel right now. And don't forget to subscribe on this YouTube channel as well to follow the other communities events such as GDGs, WTMs, and DSCs like us. As Musa mentioned, I have shared the link tree of the SC Medipol. You can join to our WhatsApp groups and follow us on Instagram, Twitter, LinkedIn. That's all.
Yeah, then I would like to thank for every of you guys for taking your precious time and just being with us today. That really means a lot to us. We are also expecting you tomorrow in the tomorrow's sessions. So yeah, try not to miss them. They're going to be actually too fun.
Yes. Okay, take care. Thank you very much. Thanks for joining us today. See you.
Thank you.
See you guys. See you tomorrow.
Thank you.